Okay, I'm recording now. Good. Okay, the first thing I want to say is that some of you have not sent me in your hours of the internship yet. So please do that if you haven't told me how many hours you've done on internship, so that I can make an assessment and decide what we're going to do moving forward, because it seems like the whole idea of an actual internship in a place is going to be difficult because of the coronavirus going around. And so I have to think of alternatives as we get closer to the fall semester when that course is embedded, all right? I'm thinking of some alternatives, but I want to know how much hours each one has. And it could be from very little to a lot. Some of you were proactive and got with it early on back in December, January when I announced it. And so you've done quite a few hours. Others have not done that many. So I want to see those numbers individually, please. Okay, just send me an email telling me just overall how many hours you've done, even if it's in different types of internships. Okay. All right, any questions or comments about that? No? All right. Okay. Any questions or comments about anything previous? No? Okay. So we still have about 3 more lectures, being that we postponed them, remember, from the beginning of the summer due to the emphasis on stats. So now that that is out of the way, we can concentrate on this environmental bioethics course and get it out of the way too, all right? Okay, also to let you know that I'm recording now at St. Thomas University because I didn't want to risk the issues of the internet over there at Monica Parish. We're having issues, as you know, in the previous Saturday, so hopefully this connection will be nice and clean throughout the entire morning, all right?
Father?
Yes?
Father, if I could just interrupt for a minute. I'm getting a text from Ada saying she can't hear. I'm hearing fine. I just wonder if everybody else can hear or what the issue might be.
I can hear fine.
Yeah, I can hear fine.
Clearly, yeah, I can hear fine.
Okay.
All right, I'm going to let her know we can all hear, so it must be on her end.
Yes, yes.
Okay.
It seems that way, yeah.
Okay.
All right, thanks a lot. Let's see what else. Okay, so let's move forward then. So today's lecture is on energy, and to put it in context, this is what's happening up until now. You see the 4 lectures that we've had, the one on the geosphere, the atmosphere, the hydrosphere, and then the last one on cycles, natural cycles, and human recycling. Really, it's all been on matter, right? On material, on stuff, in its 3 states, in its 3 natural states that we find matter on Earth and in the universe, which is solid, liquid, and gas. All right, so there's kind of a an infrastructure to this, if you will, that we looked at the geosphere, the solids, the atmosphere, the gas component, and the hydrosphere, the liquid component of Earth. Then we look at cycles in nature and recycling of, again, matter, solids, liquids, and gas, right? And the different cycles that we saw. So now we're going to look at energy, which is a little less evident, if you will, from nature, but truly it's the possibility of life is due to energy at the end of the day, because this energy is the fuel for metabolism. And metabolism translates into organic living, all right? Including the functioning of the brain, of any brain. And so we're going to look at energy, and also because it has bioethical impact due to the issue of climate change and global warming and the burning of fossil fuels, which is the biggest offender. That's why in the last cycle, the last lecture, one of the major cycles that I wanted to point out there was the carbon and carbon dioxide cycle, right? Because of the net increase in CO2 in the past decades that is anthropogenic. Anyone remember that figure? After we looked at all the CO2 cycling and recycling from cellular respiration to photosynthesis and other burning of fossil fuel, and then also volcanic activity, etc., and the sinking of carbon and deposition. After all that budget is set and done on an annual basis, anyone remember if we, at the end of a year, we have more or less CO2 than the previous year in the atmosphere? Just the basic question, at the end of any year recently, in the past decades, right? At the end of each year, do we have more or less CO2 in the atmosphere?
It was more.
More, exactly. We have more, and that's a recent phenomenon, all right? It's a recent phenomenon. Unless we go back to the primitive Earth when there was a lot of volcanic activity and the primitive atmosphere was very different to ours, it was toxic. The current atmosphere really has very little CO2. Remember, it's about 98% of a 0.1% of the atmosphere by volume. And so there's very little CO2, but that CO2 happens to be a greenhouse gas. What do we mean by greenhouse gas?
It comes from the sun, right? That process?
Well, no, not necessarily. I'm talking about the molecule of CO2. It retains heat, right? A greenhouse gas, it retains heat because, so it has the same effect as a greenhouse. If you've ever lived up north, or you've seen movies about houses up north, they have these greenhouses, which are glass houses, and light gets through, and as it hits surfaces, some of that light bounces off, and other of that light is transformed into heat. And the light goes through the glass, but the heat is retained inside the glass house. And so it's warmer inside those glass houses. And therefore people are able to grow and maintain plants in the wintertime when it's snow outside and all the trees are barren. Inside the greenhouse, it's nice and warm, and the plants are nice and green, okay? There are some gases that have that same effect. And one of them is CO2, has, again, like water, has a high heat capacity and retains heat. Methane is another one, and there are a few other gases. But the biggest one, the biggest culprit, if you will, of global warming is CO2 in the atmosphere. And the number that I was looking for is 4 gigatons of the 9 gigatons of CO2 that are produced by industry, mostly by industry, by burning what? By burning fossil fuels, right? By burning fossil fuels. Well, of those 9 or 10 gigatons more or less that are produced on an annual basis at the level of the whole world, about 5 of those gigatons are reabsorbed by photosynthesis, whether it's on land or in the oceans, mostly by the phytoplankton, right? So about half of our excess of our anthropogenic CO2 production, nature is able to handle and absorb and sink it, carbon sinking into the soil, into the ground, so that it's not CO2 anymore, or transform it into glucose, which is actually energy, or other carbohydrates, all right? So that's chemical energy. So what do I mean by anthropogenic? generated by the human. Genic, generation, genesis, genetics is the beginning, all right, or the generation of, the production of, the manufacturing. Anthropos is a reference to the human. Remember when we looked at the anthropology of the human species, the origin of the human species? So anthropogenic means that we are producing, right? There's one species that produces, not only produces a lot of waste, but also produces CO2, mostly again through industry throughout the world by burning of fossil fuels. And so we have that net excess of those 4 or 5 gigatons a year that are slowly accumulating in the atmosphere and are slowly warming up the atmosphere. So that's your global warming there. Then how it's distributed throughout the world has a lot to do with the patterns, with the wind patterns and the Hadley cells and all this that you should be thoroughly familiar with by now because of the previous lectures on how the wind pattern gets around. And even mixing into the ocean, because CO2 is also soluble in water, it turns water acidic, all right? So that's the ocean acidification that we'll see more of in further lectures. So it has a double effect. It has an effect of a global warming on the atmosphere, and it has an acidification effect on the oceans, which is by volume 90% of the surface of the earth, with all the biodiversity being affected by that acidification, all right? Okay, so bottom line about all this is that it puts fossil fuels in a bad rap, and we need to think of alternatives for energy sources. And we are a species that uses a lot of energy to run our industry, to run our transportation, to run our housing, to run our air conditioning, and everything that makes us livable on this planet, okay? Okay, so that's kind of the background why we need to look at energy then, energy production and consumption. And then we'll finish up again, as always, with the more ethical, the bioethical aspect of a natural right to energy, because we need energy to live as humans, not just in the jungle, all right, but to live as humans in a civilized way. All right, let's move forward then. So we're going to go through these different types of energies. Some are renewable, some are non-renewable. And that's one of the key factors here, at least from the bioethics perspective, what's renewable and what's not renewable. Okay. All right. Again, if there are comments or questions anytime, stop me along the way. Otherwise, I'll just keep going. All right. So we can divide energy sources into 2 types, whether they are renewable or non-renewable. And of course, the non-renewable are using up resources of the earth, and we should try to wean away from the non-renewable energy sources. Also because, so for 2 reasons. First of all, they are using up resources of the world. And secondly, more importantly, really, is the production of CO2 or nuclear waste that these 2 non-renewable sources produce. Whereas renewable, the word speaks for itself, all these other different sources of energy are renewable in nature, or we have such an abundant source, like primary source of it, that really it doesn't make a bit of difference for the source of the energy if we're using up that source. For example, I'm thinking of solar, for example, light energy from the sun. Of course, we're using up sun energy, solar energy, light from the sun, sunlight with solar, but we get such an excessive amount of solar energy, of sunlight on a daily basis that running the photocells on that, the consumption of that energy is absolutely negligible compared to the huge amount of sunlight that the sun puts out on a daily basis, okay? All right, getting a little ahead of myself here, but basically, so for non-renewable, we have the fossil fuels and nuclear. For fossil fuels, Again, the three states of nature of matter: coal in the solid state, petroleum in the liquid, thick liquid state of petroleum, or we also know it commonly as oil, and then natural gas. Then for renewable, solar, wind, hydroelectric, geothermal, wood biomass, fuel biomass, and then others, which kind of ranked by percentage here. But so you see there are more renewable sources of energy than non-renewable, but they're still fairly new and they have not been introduced as much into industry, mostly industry, which is the one that uses most of the energy, and somewhat transportation would be a second, because they're still more expensive to obtain, okay? All right, so let's move forward then, looking at the non-renewable, which is gonna go through them one by one. Looking at fossil fuels, what do we have? We have coal, we have petroleum, and we have natural gas, okay? Now, the issue with fossil fuels is that it's based on carbon in different shapes, carbon solid, coal, or carbon as a thick liquid in petroleum, or carbon as natural gas. So these are carbohydrates, those carbohydrates, and the carbon-carbon bond, that covalent bond of carbon to carbon, the backbone, the skeleton of the structure of these carbohydrate molecules, those carbon to carbon bonds, covalent bonds, are high energy bonds. So when those bonds are broken, then a lot of energy is released. Energy that can be trapped and used for work, for generating electricity typically, and then the electricity will run the factory, will run the industry, will run the transportation, and so forth, okay? So it comes down to the carbon-carbon bonds in carbohydrates, and these are known as fossil fuels because they come from fossils, mostly forests, huge forests. During the tropicalization of the Earth, you remember in the past 500,000 years alone, the 4 ice ages that we've had on Earth, right? Those are winterizations. But then when in the interglacial periods, where the temperature, where the mean temperature of the world went high, you know, to the 30s in centigrade, to the 90s, maybe 100 in the Fahrenheit, then the Earth was tropicalized, right? Meaning that there were lush vegetation, lush forests, tropical rainforests throughout the whole world, mostly again in the Northern Hemisphere, because that's where most of the land mass is, just pulling out from previous lectures. And to give you a graphic example, you think of Alaska, right? Today, which is very cold, has glaciers, has a lot of snow, a lot of ice. But there's also oil in Alaska, right? Meaning petroleum. There's petroleum in Alaska, okay? And so that petroleum is fossil fuel. Those are forests that got buried over the millennia and crushed and compressed into petroleum. And if we continue to compress petroleum, that black gunk eventually it solidifies into coal, right? And those forests that were in Alaska were tropical rainforests. That oil, that petroleum in Alaska, and that coal in Alaska comes from tropical rainforests. So how can Alaska be tropical? Again, because of these interglacial periods. So we tend to think of ice ages as the whole Earth winterizing and becoming very cold with ice sheets on top of it, glaciers that cover the entire continents. But the in-between stages, because of these cycles, these natural cycles, the in-between stages when it's been warm in the interglacial periods, right? the Earth has actually been tropicalized. And so vast forests throughout the world that with the winterization eventually died and were crunched down into the earth. That is what has become the sources of coal, shale, and petroleum, and even natural gas, all right? So that's why they're called fossil fuels, because they come from fossils. But the animal also, when we talk about fossils, the human mind just tends to think of dinosaurs and animal fossils. But plant fossils are much larger in volume, much larger in volume than animal fossils, okay? Just think mentally of any forest, and most of the living creatures in a forest is plant material, it's not animal material. There'll be some animals in there for sure, but most of the material in a forest, most of the living material is plants, okay? So these fossil fuels are mostly forests, typically rainforests that got crunched together, 500,000 to previous, even in previous, I mean, these 4 ice ages just in the past 500,000 years, but we can go further back because the Earth has about 4.5 billion years, right, of existence. And for about 4 billion years, more or less, we've already have life on Earth. So these fossils have been accumulating over millennia, over millions of years into the Earth, into the crust of the Earth. And that is overall these fossil fuels. Okay. So
Father, can I ask a question?
Please.
So you're saying when these forests were crunched into the earth over what, hundreds of thousands or millions of years, I guess they became oil, the liquid form?
Yes, they
And
rotted,
then-
basically. Yes, exactly. So
And
thank
then
you for,
was it further pressure that created the coal and the gas?
yes.
Or just time, or both?
Both. Time and pressure, you know, more sedimentation on top of the crust that crunches that petroleum further. So if we start just with the petroleum, the black gunk, right? This
Right.
is essentially a rotten forest.
Okay.
It's a rotten forest that eventually turns black, thick liquid, all right? Very rich in carbohydrates, very rich in different types of oils and so forth. If we continue to compress that, it starts separating. Some of it becomes gas, some of it becomes solid. So that's where we get the natural gas, and the solid component is the coal. In fact, if we continue to compress coal, eventually what do we get when we compress coal down to its crystalline structure?
Girl's best friend.
That's right, the girl's best friend, diamond. Yes, diamonds are a pure crystal of carbon, okay?
Okay, one more question. I'm sorry. When you said earlier about the covalent bonds, which are carbon to carbon, carbon bonded to carbon, and you said something about how when that bond is broken, the energy is released.
Yes.
Can you just say that one more time? Because I didn't quite get that. And
Sure. So these are carbon to carbon bonds are typically the skeleton or the infrastructure of carbohydrates, right? Think of glucose, for example, the 6 carbons in a string, that's a carbohydrate. And so when those carbon to carbon bonds are broken, then this energy is released, fairly high energy, because those are covalent bonds that have high energy bonds. That's what we call chemical energy. All right.
Okay, I'm sorry, is that bond something that happens naturally, or is that something that we do to get the energy?
Right. Okay. So it happens naturally, and we do it by burning. But nature does it also by burning, which is cellular respiration.
Okay, burning does it. Okay.
Exactly. Cellular respiration. Another word for cellular respiration is burning glucose. But it's the burning is done in a controlled reaction, in a controlled way at the cellular level, so that there's no flame. Okay, there's no flame. But burning glucose, you know, cellular respiration is essentially breaking glucose. What we're doing is by adding oxygen, the reactant to that glucose molecule, the glucose molecule is broken. First of all, it's broken in half into 3 carbon, and then further broken down, and that's where we get the CO2. You know, the C of the CO2, the carbon of the CO2 comes from the breaking of the glucose, okay? So that's how we get that, that the cell, nature does that by cellular respiration, and that's the way of nature to get energy from carbohydrates, burning carbohydrates, all right? Like we talk about burning calories. And that energy is then used for metabolism, for running other metabolic processes of the cell, of the tissues of our body, of the organs, and that keeps us all alive. All right, and then the converse process of that, that's what we saw, that redox reaction, the back and forth. Nature also takes up CO2 then, which is a waste product of the burning, takes up CO2 from the atmosphere and combines it with water from the soil to remake the carbohydrate molecule, which is the glucose, and that is done by the complementary process of photosynthesis. And that's why cellular respiration and photosynthesis are reactions going in opposite directions. The starting products of one are the ending products of the other, and vice versa, okay? So nature has figured it out that there's a balance, there's a beautiful, elegant balance in nature between cellular respiration and photosynthesis. But then what happened to nature? We landed on nature. We landed on Earth, figuratively speaking. And so in our own industrious ways, you know, we have become so industrious, in fact, as a species, that we're altering that balance. And we can distill it down, if you will, to these 4 gigatons of CO2 that we're producing every year in excess of what nature can handle. So since we are the ones who are producing that excess, we need to deal with it. Because if we don't, in the end, it will be our own destruction, and it will be the destruction of the rest of nature also. Right? Okay, so the issue of bioethics here is grave, is urgent, and it's real. Okay, so fossil fuels are the big ones that are producing most of the CO2 in excess of the natural CO2 that's produced through respiration. Okay, and that's why this urgency that you see throughout the world in trying to replace fossil fuels with alternative energy sources, All these are buzzwords and buzz phrases are being thrown around. They get politicized and all that. We need to try to cut through and get to the science of it, which is really where the hope at the material level would be. Okay, so I think we know enough about fossil fuels, coal, petroleum, and gas, natural gas. This, by the way, is called strip mining, which is just getting on a mountainside that is very rich in coal and stripping it away, just with heavy machinery, excavators and truckloads, just hauling it out to the factory where that coal is burned to generate a heat, and then the heat moves turbines to generate electricity. Now, don't be deceived. A lot of these clouds that you see here, this is not CO2, okay? This is typically water vapor that is being released from the steam engines that are running the turbines. So at least in the United States, this is, of course, highly illegal if it were CO2. No, this is really water vapor. The same we'll see with nuclear energy because water is heated up in the process of generating electricity. Okay, let's move forward here. Okay, this explains a little more detail what I was talking about. The whole issue is about generating steam, all right? Generating steam to turn a turbine. So here's the coal that is burned. The coal is burned in this furnace, and this furnace or boiler heats up water to make steam out of it, and the steam will then run the turbine. A turbine basically is a rotating machine, and in the rotation of that machine, it generates electricity. Something kind of similar to friction when we rub our hands together, or at night in the cold winter, or up north, if you shake the blanket, you see the little sparks coming out, right? Those are like mini lightning bolts taking place in your bedroom there. That's static electricity that is caused by friction. So what happens here is when the turbine turns, there are poles in here, positive and negative poles, that generate electricity. And that electricity can be pumped into the grid, all right, for use, either industrial, commercial, or even for individual households, etc. So the whole idea is to use coal to burn it, to heat up water so that steam is generated, and that steam will then at high pressure turn the turbine, and the turbine by turning will generate electricity, and the electricity is pumped into the grid, the electric grid, all right? The waste products are, well, steam. That steam then is released into the atmosphere. It's just water vapor, which eventually will go into the clouds, okay? But the other issue here is the burning of the coal, which generates the CO2. So that's where these filters are crucial, because these filters trap some of the CO2 so that the emission is minimal, but still significant, all right? And these filters, by the way, typically is also carbon. So the coal is carbon, the CO2 generated by burning is also carbon. And the filters are carbon, is known as activated charcoal, so charcoal that has been kind of electrified, all right, is used to trap the CO2, but it's not 100%, all right? It would be extremely expensive. It would not be cost effective if we were to trap 100% of the CO2. So there's that little bit of emission that is part of the contributing factor for that, the 4 gigatons on the annual budget of CO2. All right, so that's coal. Fracking, I want to talk a little bit about fracking, because also it's been in the news, not so much lately, but going back a little bit, it was controversial. I want you to understand fracking to see the risk and the benefits, because sometimes these things get bad rep in the news. But my experience with secular news is that typically they don't really know what they're talking about, but it's sensational and they pump it out there because it sells. All right, so fracking is actually a contraction of hydraulic fracturing. Again, the big picture is this, that deep down into the crust, we're talking 1, 2, 3 miles down, there are layers. You see the sedimentation layers here, okay? For example, this is the soil layer, and then below that is sedimentation, sedimentary rock, which tends to be porous, and that's where we have the aquifers. These blue lines, they represent aquifers and groundwater that we talked about in previous lectures, right? More sedimentation. Eventually we get down to where the carbohydrates are stored, shale and coal and natural gas are in this lower layer. So you see all the compression that has gone on. And look at the scale, okay? This would be like a factory of fractioning here, or yeah, a station. And we're talking 1, 2, 3 miles down into the crust. So there's a lot of compression going on here. It's under high pressure. All right, so what do we have? The coal is there, but also in the coal, there is this shale that is a mixture of rock and natural gas. And the gas is in there and it's kind of trapped, this natural gas. So what fracking is trying to do is going down with pipes into that area vertically, again, 1 to 2 miles down, and then horizontally into the layer of coal or into the layer of shale, all right? And there, what is pumped through this hole, through these pipes, what is pumped through these pipes is a brine that is made up of water plus minerals plus sand, okay? And that brine is pumped in there under pressure and gets into the cracks and opens up these cracks. By opening up the cracks, it releases the gas that is there, natural gas that is trapped in these cracks, okay? And so there's a little diagram where the water is pumped under high pressure, that the fluids and the sand and the minerals get in there and open the fractures somewhat so that the gas is released, escapes, and the gas will then go into the solution and be recovered with a backflow back up the same pipe, right? This like a double pipe, there's an inner pipe and then there's an outer pipe, a sleeve, if you will. And there's a backflow coming back up to the station where that water is recovered and the gas is extracted. The gas is extracted. Then that brine that flows back is dirty, has to be cleaned up and so forth. So the positive of fracking is that it has access to oil and natural gas that is not accessible through a natural well for petroleum, okay? Because
Or
that,
could you, excuse me, Father, could you go back a little bit? What are some of the dangers of fracking, since you say some of the costs are sensationalized in the media?
yeah, I haven't gotten there yet. I'm still talking about the science, okay? So,
Well, excuse me, Father. So you're talking about the science. So, okay, never mind.
okay, so I'm getting there. I'm talking about the benefits first, then the dangers or the negatives, if you will. So the positives is that we can get natural gas and oil from this fracking process, okay? Now, the negatives is that this activity, by loosening up these fractions here, there's fractures, and getting out some of the gas that is under high pressure and trapped there, it causes seismic waves, it causes earthquakes. And that seismic wave transmits through the sediment up to the surface and can cause some earthquakes. That's one that has been felt in some towns. This is done typically in rural areas. I'm talking about the United States in particular, also because it happens that a few years ago, vast resources of natural gas have been found in the United States, mostly in the Midwest, in the middle of the two mountain ranges between the Rockies and the Appalachian Mountains, okay? The big, vast center of the United States is mostly flat, the Great Plains. There's a lot of sedimentation there because that used to be an ocean way back, the Mississippi Sea. During the tropicalization of the Earth, precisely when the oceans, the sea level was 100 to 200 meters higher than what it is today, okay? And so the bottom line is that there's a lot of natural gas and oil in general in the Midwest just accumulated there. And so fracking is one way to get at it. But it does cause those seismic waves that can reach the surface and cause some earthquakes or tremors. Earthquakes is a little too strong of a word for it because they're not comparable in magnitude with natural earthquakes that occur, for example, even along the Rocky Mountains, or the friction of tectonic plates that we talked about also way back in the geosphere lecture, all right? So they're not in the same magnitude, order of magnitude, but it can cause some tremors on the surface. So that's obviously one negative, especially if there are towns nearby. Another negative is that there could be contamination along the way in the process. Some of that gas that is being released from the fractions, instead of going into the pipe, may just seep through the sedimentation layer and contaminate the groundwater, which is typically the water that is used eventually for drinking and for washing and so forth. So some of that can contaminate the groundwater. Also, pipes can have breaks, just like petroleum pipes can have breaks, and there will be leakage there. And also, some of the natural gas will be methane, and some of that methane can be released to the atmosphere. And this is also a greenhouse gas, a warming gas, okay? So some of the negatives are those.
So, Father, excuse me, how can you say that the secular media sensationalizes those things? Right underneath the demonstration, the illustration you're using on fracking for oil, they list some of the things you talk about, but there's 15 things. Why do you say the media has sensationalized it?
Yeah, because some of the media has. I really don't have time to go into the videos that were later found fraudulent, like one in particular that someone was opening a faucet, and out of the faucet came actually gas, and they put a match next to the faucet. Instead of getting water out of the faucet, they got a flame. And later it was discovered that that gas, which was natural gas, was being produced by bacteria, was not due to fracking at all. Okay, but you know, hold on a second. There's some chats here also that I want to read. Okay, Marie, can the gas be released on its own? Okay, Maria, not on its own. Gas can more easily be released through distilling fossil fuels and cow farts. Okay. All right, yes. So some of the gas can be released on its own, yes, but the problem is, for us, is that it's so deep down. You know, we're talking about a couple miles down into the crust of the earth. All right, so to get down there, and this gas, some of it does seep through naturally, but it takes a long time. And as it seeps through, it's dissipated. In fact, it seeps through on its own, and it's going to contaminate the water table and so forth. But the sedimentation layers prevent that. Okay, so
Father,
anyway,
can this cause like sinkholes, or is that caused by something else?
no, this is way too deep for a sinkhole. A sinkhole is really at this level here.
Oh, okay.
All right, and the soil giving in to some water, if the water displaces and the sedimentation layer between the water, let's say an aquifer, and the soil on which we stand, if that sedimentation layer is thin or fragile, it will give. If this water is moving, because these are also underground streams and rivers that are moving, okay? And so you get a sinkhole if this little thin sedimentation layer gives. But
Okay.
it's really at a very shallow level compared to what we're talking about here, way down.
Okay, thank you.
The scale, right? Look at the scale. This is
Yeah.
a station here. Okay, someone else had another chat. Hold on. Okay.
Well, Father, no, going down on the, and again, underneath the illustration that you use for fracking for fuel, it also mentions further down in the article that each well can require up to 8 million gallons of water and up to 40,000 gallons of chemical. A well site may need up to 2,000 tanker trucks. As you mentioned, the storage of the water can cause open pollution, and then also the release of methane, which is apparently one of the most dangerous, 25 times more potent. So if people go to your site there, the Fracking for Oil illustration, there's a large article underneath it that might be pertinent.
Right. Yes, but you notice that invariably we're talking about technology, right? In other words, with better technology, we can better handle the contamination issue, the leakage issue, and so forth. So these are mostly technological issues. The methane also can be controlled better by filters and so forth. All I'm saying is that as far as a resource, as a natural resource, it's there. We have one of the largest deposits of natural gas. We just happen to have that because the United States is sitting on the northern plate, right? The north plate. and it has one of the largest deposits of natural gas that is sitting there. So possibly, if this fracturing technology can be cleaned up, if you will, by the proper technology, by the proper filters and so forth, it's a potential that we have of an energy source that is considered to be one of the largest, most vast resources in the entire world of natural gas, okay? But again, it's a fossil fuel, so even with the best technology, if hypothetically we can bring down this to zero or negligible contamination, it's still a non-renewable resource. So eventually, if and when we use that natural gas, it's gone. So even in the long term, hypothetically, if we were to clean up the industry so that it would be, so that the contamination would be really negligible, you know, not above what, then there is natural methane that's being released into the atmosphere just by nature, okay? Even in the best case scenario, the resource is not renewable. So eventually we would run out of it. All right? So it's still
Father,
moving that into non-renewable, into a renewable resource.
Father, I think regardless if the technology improves by leaps and bounds,
Yep.
the enormous amount of water that it takes for this to occur and the safety at the workplace, to me, just doesn't, you know,
Right.
provide this as a good method. I mean, we could tap into solar and wind, which will not affect human life. Or, I mean, as we fight already for oil in the Middle East, just imagine when we start fighting for water. So regardless of this getting, you know, so hunky-dory and awesome in the future, the risks are still way too enormous for this to even
the difficulty is projecting into the future with the current problems, right? With the current issues. You know, we can look at the pandemic right now that we're living for an extended period of time. Extended is 6 months and we can't stand it anymore, but who knows what the world is going to be in a year or 2 years from now. Is it going to be now, from now forward, for the rest of the existence of humanity, we will have to wear a mask as soon as we step out the door, okay? Those are big unknown questions. But yeah, it's hard to imagine, but I can tell you that there's so much potential money in this, all right, because it's so cheap. We get so much out of natural gas that the industry is pumping money into it to make it safe, is all I'm saying. It's a natural resource that is there. And with regards to the water, consider again that by volume, 90% of the surface of the earth by volume is actually water, all right? And so we do have potentially a lot of the material that is needed to get at this natural gas.
Father, I mean, 97% of the water is salt water. They are not using salt water, as far as I know, to use for fracking. As you pointed out, 3% of the rest of the water is available to the population, and not all of that is even available. I think you're being really far too generous to fracking, regardless of the technical advances. From what Ada was just saying, I think this is almost morally immoral and unethical to look at fracking like this. And the only people who are really going to make a lot of money is the oil and chemical industry, not people, and certainly not people across the world who are suffering from our energy use across the rest of the world.
Okay, so obviously we have differences of opinion here on how we evaluate and how we do the analysis. I just wanted to present to you mostly the science part of it. You can research it further, of course, at your will, all right? But because it is one of the sources of non-renewable energy, non-renewable energy, then I just gave this one slide to fracking so that at least you have a basic understanding of it. I want to move forward now to looking at an overall balance, budget of petroleum, all right, and how it's used, so that we have a more accurate understanding on how petroleum is actually used in industry, at least in the US, all right? So almost half of it is used for gasoline, and then about 10% is jet fuel, because jet fuel is more refined and so forth, more high energy, being that airplanes have to optimize for weight and volume and so forth. So jet fuel is a different category than just ordinary gasoline. But between these two, you can see that more than half is used for fuel. Then another quarter, more or less, is used for diesel, which is a cheaper type of fuel. So really, about 80%, 75, 3/4 of the petroleum is used for fuels, okay? Now, some of this fuel is used in transportation directly, but a lot of it is also used for running industry, for running machinery, all right? So fuel doesn't necessarily mean that it's transportation as such. A lot of this is actually used in industry for running the machinery that makes all the products that we use on a daily basis. All right, and then just to complete the picture here, asphalt also comes from petroleum, about 3%, fuel oil, 4%, lubricants, 1%. This also is important because a lot of the industry and commerce uses these lubricants that come out of petroleum. So about 1% of petroleum is used for lubricants. And then this other 10, 11%, this 1/10 of petroleum, other products, this is mostly the plastics. All right, the plastics, again, that we use, especially the single-use plastics and all that, is contaminating the world. As I pointed out in the last lecture, this is about 10%, more or less, 1/10 of the petroleum that is being refined today is mostly the plastics that we use, okay? All right, I want to move forward because this whole lecture is not on fossil fuels, it's on all kinds of energy. So I want to look at another type of non-renewable energy that is nuclear energy, And this is in the past 50 years or so, 60 years, since nuclear energy was able to be harnessed. Remember, I think I've told you, with just two brothers, and my brother went in 1970, in 1969, actually, he went to study physics. We were living in Mexico City at that time. And he's a year older, a year and a half older than me. So he finished high school a year before, and he wanted to study nuclear physics. So he came to the States and he went to University of New York. The state university system is called SUNY, State University of New York state system, in Stony Brook, New York. And I remember that as a teenager he was telling me the story. He had gone to Stony Brook because Stony Brook was the only university at that time, I think it was like 68, 69, that had a nuclear reactor for educational purposes. All right, the only university in the US that had a nuclear reactor for educational purposes. All the other nuclear reactors at that time, here in the 60s, were military purpose, okay, or research, but classified and so forth. So it was very new. And he went out there. Eventually, he changed majors into political science and so forth. But Stony Brook back then was the only university that had a nuclear reactor for educational purposes. Anyway, that was the 70s, and the 80s was the big time for nuclear reactors. And then also the time for some horrible accidents that happened in the nuclear reactors. You may remember 3 Mile Island. Some of you may go back that far to remembering 3 Mile Island, the meltdown that happened there. Chernobyl also in Russia in the early mid-80s. And then more recently, I think it was 2012 or something like that, Fukushima in Japan, all right? These were nuclear accidents. This last one, I'm less familiar with these older ones, but this one at least was because of a tsunami that hit the shore where the nuclear reactor was built. And one of the cores broke down and leaked some nuclear fuel into the Pacific Ocean, and then with a big gyre started wandering around the gyre, got hold of that nuclear fuel and distributed. But of course, as it distributed throughout the whole Atlantic, it dissipated entirely, and thanks be to God, it lost its impact, because that nuclear fuel that was released got dissipated throughout the entire Pacific Ocean eventually. So because of these accidents, it became unpopular to use nuclear power as a source, but I can tell you it has a high capacity for generating electricity, especially, all right? You can see in this graph, this was what they call the installed capacity. In other words, the theoretical capacity. You can read these as the theoretical or hypothetical capacity of the nuclear reactors, and the actual capacity in practice when they were running. Because also these reactors, they're not run on full capacity, all right? They're run typically at anywhere, I'm gonna guess between 60–80% of their capacity, not really full capacity. So, but that's what they're putting out in gigatons of gigawatts of electricity. So for a relatively small amount of nuclear material, uranium and other nuclear reactive material, they can release tremendous amounts of electricity. They can generate amounts of electricity, okay? Also, I want to point out that these generators, these nuclear reactors, have gone through several generations of building and engineering. And we're up to the 4th generation now, which is the latest. I'll talk about the 5th in a minute. But these accidents were mostly 1st and 2nd generation reactors. So they were all reactors. They were actually outdated reactors. Maybe Fukushima was 3rd generation, but they should have been retired, all right, because they were old and outdated reactors. This is an example of a 3rd generation reactor. Again, I want to point out that essentially what the nuclear power does is it heats up water. That's why typically they're next to rivers or they're next to the ocean, because the water is needed to be heated up and to run turbines, and the turbines are the ones that generate electricity, okay? So it's not the nuclear power itself, it's not the actual uranium that is generating the electricity, it's actually the steam. The nuclear power is used for heating up water under controlled conditions, and then that steam that is generated there is the one that runs the turbines. And that's why you see these huge stacks that are cooling towers, all right? So again, I want to point out that this is not CO2 that is being released to the atmosphere. This is actually just steam, it's water vapor that will eventually incorporate into the clouds of that region. Because these water towers are used to cool down the water that was used to run the turbines that are in here somewhere, all right? I mentioned now we're up to, so even the 3rd generation are outdated now. We're into 4th generation nuclear reactors, nuclear power plants, and you can see that these are totally clean. They don't even put out the steam. So these are more efficient. The engineering has been done so that there's more redundancy, and the rods, the nuclear rods actually close down and shut down way before there will be any danger of leakage. They're all contained, and they have systems of redundancy, sometimes 4 and 5 levels of redundancy to shut down if there is any kind of event that can threaten a leakage of the nuclear material, okay? They even recycle the rods now, or they bury them deep down into the soil, into the earth. So the 4th generation reactors are much safer than the previous generation and cleaner and so forth. And in drawing, there are 5th generation reactors also that are being designed already. The engineering is done. They're still only theoretical, in other words, in plans, but engineers and nuclear physicists and nuclear scientists are already working on 5th generation reactors, which the rods apparently are totally recyclable, and they're even more safe and more efficiency. What they're trying to get is more efficiency out of the nuclear use, okay, of the nuclear reaction. Okay, so just to mention that right now nuclear reaction building has stabilized, and there are some new ones projected, but very few, especially after Fukushima. Again, it got bad rap and so forth. So in the public mind, this is very dangerous. However, looking at the science and the current generation of reactors, it is far less dangerous than the general public perceives a nuclear power plant to be, all right? What does need to happen, of course, is that the previous generation reactors definitely need to be retired and shut down because they're obsolete at this point. But this is where we're at right now. I have seen some reports and some claims that while we make the transition from fossil fuels to non-renewable resources, which in general tend to be more expensive, the non-renewable, the renewable resources like solar and wind and biofuel that we'll see in a few minutes, you know, the transition while we go from fossil fuel to totally renewable could be nuclear, because it can generate the wattage that is needed for running the industry that we run in the United States and in the world, especially the industrialized world, as we wean off of fossil fuels. Okay, so one possibility is that a nuclear could at least hold us over until we get into totally renewable resources. Because even in the best case scenario that these new generation reactors are totally clean and safe and so forth, we're still using a non-renewable resource. So eventually the uranium and the nuclear material either runs out or gets more and more expensive and more difficult to extract and to purify, okay? All right. Let's look at another budget here. Now making the transition from non-renewable to renewable. Here's a graph that is pointing out, since we started as an independent nation, pretty much the past 250 years, more or less, that we have of history, the different energy sources that we've used, that the United States has used in the past 250 years, again, trying to look at the bigger picture in the US, all right? You can see that for the first 100 years, more or less, it was wood. In other words, go back to the 1700s, how food was being cooked, how water was being heated and boiled and so forth. Basically, cottage industry, it was mostly by burning wood, all right? Even just a campfire, keeping people, or the chimney, the fireplace, etc., keeping people warm in the winter. So it was mostly wood. Then, about 200 years ago, we started mining coal, and that became the big thing for at least 50 years or so. Burning coal was a big industry because we could get a lot of energy from that. Again, mostly the steam engine, right, which this also parallels the Industrial Revolution and the invention of the steam engine. Basically, by boiling water, we get that steam that under pressure can then run machines. Through the turbine, it can generate electricity, and also the steam engine can run paddles and wheels and helices to move cars and trains and ships and whatnot, okay? Then we start getting into petroleum, which is this middle brown here, and refining petroleum and using that. So slowly you can see that petroleum replaced coal in general as the main source of energy for the US. And then the refinement process was available for natural gas, which again started replacing petroleum, mostly for industry. Okay, the large amount of use, if you will, consumption of these sources is to run industry, right? To run all the machinery that produces all the products that we use on a daily basis, including the big machinery that makes cars and trains and all that, the steel, for example, right? So natural gas became more popular, more available. And then more recently, in the second half of last century, nuclear energy here with the dark blue, but it kind of stabilized also. And this one is what I'm saying could make the transition for us. But basically at this point with hydroelectric, which is the light blue, we move into renewable sources, okay? Renewable sources of energy. So you can see that up until now, to our current times, we're still using about 90% of non-renewable energy sources, mostly, and about 80% of that is mostly fossil fuels still, okay, between coal, petroleum, and gas, about 1/3 each. And a small percentage about 5% more or less from nuclear energy. And then it's only about 10% of our energy that comes from renewable sources in the US. All right, so again, this is a big picture that is historical because it gives us a perspective of about 250 years. But when you look at the curves here, it's encouraging, right? Because this definitely has a downward slope. This has a negative slope. This also has a negative slope, slightly less. This has a lesser, but still negative slope. And these are all fossil fuels. So that negative slope is a positive statement, right? Or ethically speaking. Even nuclear has a negative slope, and even hydroelectric. But what we see finally in the other renewables, the small area, that is beginning to trend positive, very slightly positive trend, all right? And this is where our emphasis really should be going forward. It's just that, again, it's expensive. And so industry is not going to go use energy sources that are more expensive than the product that they're making, because then they have to shut down, right? Because they're not making a profit. Okay, so it boils down to economy. It does boil down to economy, and that's where creativity needs to continue to work in this track here. All right.
Father, a question. I'm looking
Hello?
at.
You don't have this in a smaller size?
Sorry,
I don't know.
Marie, you need to mute your mic.
I'm looking at the hydroelectric area.
Yeah.
And it looks like it begins around 1880, something like that. So in the word hydroelectric, does electric mean it's producing electricity or it's using water and electricity to produce energy?
No. So hydroelectric is mostly damming rivers and lakes to produce electricity, okay, from running water.
Okay. What would you
running water?
Okay, what would something like, this is maybe a little off topic, but like I'm thinking of like a water wheel that like a miller would use to grind grain. Is that included in something like this, or is that completely different?
It is. It's just that it's so small, right, that these are annual budgets for the whole US.
Right.
But those water wheels for sure. And in fact, you saw the water wheel working in the Baltimore water wheel that is cleaning up the harbor, Baltimore.
Right, yeah.
Right? And they're using that water wheel as a supplement from the solar panels that they have on the roof of that thing to also generate electricity, but mostly to move that conveyor belt. Okay, so the water wheel can be used either to generate electricity, but also because water has such a powerful force. Remember, liquid water is essentially incompressible. Water flowing down will continue to move relentlessly. So that paddle can be used physically to turn a conveyor belt.
Mm-hmm.
See, and that conveyor belt is doing work because it's picking up stuff from the harbor and then dumping it into a dump truck or into a container, into a trash can. Okay?
Got it. Thank you.
Mm-hmm. Yeah. So that's where creativity comes in for sure. Let's move forward a little bit with another graph, and then we'll start looking more directly into renewable resources. Okay? So let's look at how we stand with the rest of the world with regards to energy production for consumption. So the energy sources, like I mentioned earlier, in this it's another way of putting this graph in a pie shape, right? More or less 10% of our energy sources right now in the United States are renewables, about 10%. And that includes hydropower, biofuels of different kinds, wind, biomass waste, solar, and geothermal. So all these percentages, you add all these percentages up, that gives you the 100% of the 10%, okay? And these are the ones that we're going to be looking at now going forward on the lecture. But basically, that amounts to 10% of the energy sources in the US right now, which means that the other 90% is mostly fossil fuels, all right? And here we are, these are the fossil fuels, which are the greenhouse gases. They are further subdivided down, it's mostly carbon dioxide, okay? And some methane, and then nitrous oxide, but all these, and these are fluorocarbons, that also, all of these affect not only greenhouse gases that raise the, excuse me, raise the temperature of the atmosphere for global warming, but they also poke holes in the ozone layer in O3 because they're all reactive with O3, all right? And so they're double offenders, these guys. And that's why it's imperative that we move away from fossil fuels as soon as possible. But again, it has to be, the balance sheet has to pay off for industry. Otherwise, they're not gonna do it, all right? Because they cannot pay more for their energy source than the gain or the profit that they're making from the product that they're making, whatever product that is. It could be a plastic bag, that a Ziploc that we use in a kitchen, or it could be an airplane that is being made in industry.
Father, that comment, again, I mean, this may be my politics showing, but to state just as the profits or the end result can't be, that's the part of our problem with capitalism. Truly, when we say that, you know, in a bioethical world, or when we're looking at these things, maybe it isn't just capitalism and the profit and the cost have to work out. There are higher things that we should be looking at as protecting our earth. So a blanket statement, I mean, I think that's part of the issue of how people look at the issue as sort of a, you know, a bottom line spreadsheet mentality.
Yeah, I agree fully, Shaban, and that's why in the United States we have what is known as a mixed economy. We really don't have capitalism. I don't know, but I cannot point out, of the 200 nations that we have in the world approximately, I cannot point out to a single nation that has straight up capitalism, okay? Now, if anyone knows differently, I can stand corrected, and you let me know any nation in the world that you know that runs on pure capitalism. I have not seen it, but you know, I'm ignorant. We in the United States have what is known as a mixed economy, and there are many different types of mixed economies. But mixed economy essentially means that there's regulation on industry. And that's why industry is not pumping out CO2 as it used to when it was burning coal. Down here, 100 years ago, there was no regulation. And this was being pumped out. And you can see the contamination, you know, when Chicago developed went heavy into industrialization, and the railroad system in the United States fanned out from Chicago to the rest of the nation. Industry was moving so fast that the horse carcasses were just thrown out in the streets after they skinned the horse or the cow and shipped the meat out. They just threw the carcass out on the street. So we've come a long ways, right, with all that regulation, and that's what we call a mixed economy. And so we have government regulation that ultimately is run by politics, and that's why we need responsible politicians, precisely, which are all influenceable by our vote to regulate industry in the proper way, so that we don't continue to contaminate the world, and we tone it down, okay? But yeah, so this gives us then just a graphic look at these offending gases that are coming out, these greenhouse gases that are coming out of our 90% of fossil fuel consumption so far, all right? And these are the 4 major ones. Then when we compare to the rest of the world, all right, this one comparing us to the rest of the world here, what do we have? We have that we make up about 20%, 22%, so about 1/5 of the consumption of renewable, generating electricity, basically, how do I phrase this? Generating electricity, which is the big one that industry needs for running all of the machinery in the US and in the world, all right? It's about generating electricity, cheap electricity. So we are at about 22% or 1/5 compared to the rest of the world, okay? Which means that we still have a long ways to go to produce cheaper, or to produce electricity that is affordable on one hand and clean on the other hand, all right? So again, that's...
Father, do we know I don't know off the top of my head, maybe Ada knows, what percentage are we of the population of the world?
Oh, well, we can do a quick math here. Let's take 7 billion, round it off to 7 billion. So we can divide, what are we, 320 million more or less? So you can do the math, divide 320 million by 7 billion. What does that come to? Let's see.
4.3%.
4 yeah, about, yeah, we're under 5% of the world's population. Yeah. Okay, so anyway,
Father, hold 1 second. Even with such a low number, we're the 3rd worst. That's pretty bad. That's insanely bad. Such a small population. I mean, such a small percentage in reference to the world's population. We're the 3rd worst. I don't know. I think we should do better.
In what? 3rd worst in what?
In you know, technically, all of the damage we do to the environment with our consumption of, you know, coal and 19th century technology to make electricity.
Right. In other words, you're talking about specifically of the CO2 output.
I mean, definitely not. I mean, it's between burning the coal and the nuclear energy, and the fact that we are so dependent on meat and, you know, all of it. I mean, we're pretty low in the totem pole percentage-wise, but we're 3rd worst in how we just destroy this planet.
Okay, I'm not clear of what you mean by the 3rd worst. What are your units there? 3rd worst compared to that?
Percentage-wise, I mean,
China, and who's number 1?
China for sure. China, and I'll be off. Number two, I mean, I've read this not that long ago, but off the top of my head, I don't remember number two, but it always definitely made me a little
You're probably thinking of India, that's number two, and we're number three. I think you're talking mostly about CO2 production, okay, or CO2.
Oh, yeah, well, I mean, the way that we're just the worst steward, we're the third worst stewards of the planet, and we're the leaders of the free world, and, you know, our economy usually rocks, not lately, but it rocks. You know, and the fact that we should lead by example, considering, look who we are number three too. You know, I don't know, it just always made me very, very worried that such a low percentage of the population has such a bad impact. I mean, the numbers of China versus our numbers are, you know, you can't even compare. We're not in the billions over here as they are. Not to mention, we don't have the mentality of being China. I mean, China's out to get everyone else, if you truly think about it. We're not doing that, or at least we weren't. And I don't know, it just always scares me that those numbers, those statistics are always really, really frightening to me.
Okay, but I think that it's important to be clear on the units that we're talking about, okay? We're the third worst. Are we talking about crime rate? Are we talking about CO2 production?
I mean,
Are we talking about,
we're talking about BTUs
charities,
or
the
voltage
world?
or whatever. It's the amount of pollution that we let out, whether it be parts per million or whatever the case. I mean, in general.
No, you have to be more specific than that,
Okay,
because otherwise the critics will shoot you down on what is it that you're talking about. Are you talking about we're the third worst in doing charity throughout the world, for example?
No, Father,
The third worst in pollution concerning the planet, given the number of people that live on this country or in this country.
Types, okay, but the different types of pollution, again, we don't contaminate. I mean, go to Latin America. I don't know if any of you have lived there. I've lived in Latin America. There are open sewers. There are open sewers in many cities and many towns of Latin America. Just sewer running through the streets, okay? And so, when's the last time you saw open sewer running through your streets?
No, granted, we are a first world country. I'm not debating that, but I mean, in the way that we do our lifestyle is really, really concerning with such a small population in comparison to the rest of the world and how badly we pollute.
Well, okay, lifestyle, yes, we can talk about lifestyle for sure, but I'm just trying to pin you down to the units.
Oh, here, Father, I can do it. According, and this is from November 14th, 2019, anybody can Google it. China is the largest emitter of CO2 with 9.8 billion metric tons, then followed by the US, then followed by India, then Russia. So those are the numbers.
So exactly. So thank you, Siobhan, because now you put it in context. It's CO2, you know, we're worse in CO2 emission. Yes? Okay.
Yes, I think so. But I think Ada's point is, I mean, as the most developed nation in the world, you know, second to none, regardless of however, you know, we look at ourselves, we are less than a fifth of the world's population, and we create a fifth of the world's CO2 emissions and waste. I think her point isn't really talking the numbers as much as it is the overarching theory of that we are an incredibly consumptive society, and we probably more than anybody, because we are better educated, we have a higher standard of living, we lead the world supposedly in moral leadership, and this is what we are doing, is what I kind of think she's getting at and just pointing.
Yeah, so yes, so all I wanted to get was the units with which you provided, Siobhan, thank you, because it is CO2 specifically, okay? Not any other contamination, but CO2. And in CO2, yes, and it's mostly because of the heavy industry that we're running right now. And that heavy industry is making all the creature comforts that we love and enjoy on a daily basis, down to the plastic bags and the single-use plastic bottles that everybody is drinking, all right? And so that's why I'm very big on changing lifestyles precisely. And that's why I've been saying that for 50 years, I have drunk tap water in Miami, in many different parts of the city that I live, the Southwest, the Northwest, the beach, everywhere, I've drank tap water, and I'm perfectly healthy, thanks be to God. I went to the doctor just last week. I had my annual checkup, and everything is lined up perfectly. And so these plastic bottles, for example, single-use plastic bottles that everybody's drinking, that is absolutely contaminating, polluting, and it will be on their conscience. And it will be on the conscience of the people who produce those bottles, et cetera, et cetera, et cetera. So you follow my argument, right? We definitely need to change our lifestyles. Now, when are all of you going to switch your car to an electric car, for example, all right? Or ride the bicycle more often? And yes, that involves sweating because we cannot put air conditioning on the bicycle. So yes, it comes down to behavior, absolutely. Individual behavior and collective behavior, all right? So we all have still a lot to do, but as long as we're moving in the right direction, I think there's hope, right?
Well, I would also like to add that of the four countries that we named, they're also the most populous. So it's, I'm not excusing it, but it's natural in some way that we would be the biggest offenders because we have the most people to take care of.
Yeah, then you're talking statistics, you see, because
but we also
we adjust the population, and we would have to divide then those gigatons of CO2 to compare apples to apples. We would have to adjust those numbers. In other words, take the CO2 of China and divide it by its population, and then take.
I think you're going to find on a per capita basis, Maggie's argument is not quite accurate. If we only have a fifth of, I mean, just logically, if we have a fifth of the population and we are the largest emitter, our per capita number is going to go down, way down. I mean,
I was going to continue that.
We have to do those calculations to be able to really compare apples to apples, okay? Because obviously a nation that is huge and has a lot of population density, then is going to consume more electricity or more, is going to emit more CO2 per capita.
But also,
by the way, I have
as
a lecture, sorry.
Siobhan said, we have the most educated, at least one of them. And so because we have more people, we have more scientists, we have more people who are knowledgeable on this. So in that capacity, we should be looking at other resources, but not just us, the other countries who also have a large population, because it only stands to reason they also have more scientists.
Several of you have referenced several times that we're the most educated people in the world. Some people will take exception to that comment and actually say that perhaps Europe is more educated than us. In fact, when you look at university professors, for example, as kind of an indirect way or maybe direct way of seeing where the intellectual power of the nation is, or the intellectual capacity of the nation, you'll see that many university professors with terminal degrees are foreign professors, either from Europe, from China, or from India, including Eastern Europe, like Russia and so forth. So the fact that the claim that we're the most educated people in the world, some people would take exception to that statement, actually.
But if
anyway,
you
I want to move forward with the education, if I may, because otherwise we won't finish this until 3 in the afternoon. So let me move forward. We can have a little more discussion at the end when we actually touch some of the bioethical issues, okay? I want to look a little bit more at renewable energy. Finally, let's look at some of these renewable sources, which is where we want to place our hope and our technology and our talent to try to bring them forth, okay, and to develop them. So hydroelectric, first of all, which is about a fourth of the electricity generated by the renewables. It's a fourth of the renewables. Okay? So this is 25% of the 10%. This is how it runs, basically, just to understand the basic principle. Water, the river is dammed, and I understand that most rivers in the US now are dammed. They have a dam either to control the water flow, to run hydroelectrics and so forth, or even to increase navigation in the river section of it, the dammed section. But basically, the water is channeled to run through some area, some constricted area, that it goes through a turbine, okay? So that water, that flow of water on the high pressure makes the turbine turn again, and as the turbine turns, it generates electricity, and the electricity can either be stored or pumped into the grid. all right, for producing, running electricity into towns and industry, etc. So, and then the water, as it flows through the turbine, then will eventually move out downstream, and the river will continue its course. Having said this, many of these dams also, because they are natural gateways for trout and salmon, mostly salmon, and other fish to get upstream to their spawning areas. And many of these dams now, because of the ecological concern, and they have also streams, or they have some water flow that is outside of the dam proper, outside of the machinery, if you will, of the mechanism, so that mostly salmon can move upstream that way unencumbered and bypass the dam mechanism, because there's no way that the salmon can get up through the turbine, all right? Okay, so this is happening in the US, and like I say, it's about a fourth. It's the main source of the renewable energy is coming from hydroelectric plants, which is very nice and clean. But of course, it does mean damming the river or the lake to expand it, and then some areas at the coastline get flooded and so forth. So there's always plus or minus, right? And we have to weigh out the benefits and the burdens. Okay, moving forward then, let's go into biofuels, which is more recent, but also very promising because it's also a renewable one, and it has to do with agriculture. So the first biofuel that we're going to look at is just essentially ethanol alcohol, which is alcohol is a carbohydrate, high energy. You burn alcohol, you get energy out of it. So this accounts to 22%, about 1/5 of that 10% is now already coming out of biofuels, again, mostly ethanol. How does this work? This works in a slightly different process. There's really no burning as such going on. There's a fermentation process. So corn is gathered by these huge combines, right, that go through the field and gather up the corn, and they mince it, they grind it up into a pulp, and that pulp is ground up further into a mulch here, and this mulch then is fermented, right? And the fermentation process will produce alcohol, and that alcohol is distilled in a distiller. And then the ethanol is collected into tanks, which will then be used by industry, either to mix in the gasoline, for example. So you see when gas pumps now saying 5% ethanol or so forth, right? Well, this is where it's coming from. It's coming from biofuel, which is definitely renewable. One potential downside of this, and you see there's no burning, there's no steam produced, right? So it's a different process. It's by fermentation of the biomass to produce alcohol, and the alcohol is the actual fuel that is used. So this is cleaner than burning, using the steam route.
So this is basically a still making moonshine.
Yeah, exactly. In big time, okay, in big quantity. One potential downside is that now farmers are getting more for their corn for ethanol than they're getting for feed, for cattle feed, all right? So farmers, again, back to the Midwest, where we have the big breadbasket of the US, huge tracts, huge acreage of land that is being farmed. Farmers are now getting more money for the corn, for example, and other crops for making ethanol than for cattle feed. And so what is happening is that the cattle, the ranchers are hurting. In other words, manufacturing ethanol is impacting negatively the cattle industry, okay? Now, some may think that's a good thing, others may think it's a bad thing, but you know, the cattle industry is a stable industry in the US. It's a big industry, and we all like some kind of meat in some shape or form. And so it's impacting this ethanol production, biofuel production is negatively impacting for now. Again, because of the supply and demand. It comes down to the offer for corn per ton. They're getting more money for making ethanol than the cattle ranchers, okay?
You know, I don't know what kind of corn they use to make ethanol, but I know that the corn they feed stock is not the same corn that we buy at the store. It's much nastier. I've been to farms, and the farmer was taking us on a tour, and we saw a car pass by because there were acres and acres of corn.
Really?
And a couple people got out and grabbed a couple of ears of corn and kept on driving. He said, they're going to be very sorry they did that because this corn is not what they are going to expect it to be. This is corn we feed to livestock. So
yeah, it's
I don't
probably
know.
more, probably more fibrous and less tasty and so
Yeah.
forth. So
It's not pretty either. It doesn't look like it's tasty.
Yeah, it's probably smaller and so forth. Well, remember that corn originally was a grass, okay?
Yeah.
And so it's been engineered through artificial selection, and we covered artificial selection to make it big and juicy like it is today. But yeah, again, the corn feed is not as tasty or fancy as the one that we eat. Yeah. It's
one of the things that blew me away when I first got here is that Americans eat corn, because back home corn was given to chickens and other animals that we consume for nutrition. I mean, humans, or at least back home, people didn't eat corn. And then you come here, and of course there's a million recipes, and corn tastes really good. Don't get me wrong, I like it, but it's just if you really think of it from the get-go of corn, it's really bad for humans. For starters, we don't digest it. Yes, the only good thing about it is we could have it as roughage, but then you start adding all of the GMO factors to the corn and all the other things. It just, it should be maybe just left over for livestock, and at that, the worst quality of it. And then if you think about it, we consume that livestock, and there's no wonder why we're always getting sick.
Yeah, well, I do want to mention that nature, again, is a great, there's a lot of wisdom in nature and can teach us a lot if we observe it, but nature is also silent. And what I mean by this, particularly with regards to diet, is we look at our teeth structure, and we're known as heterodonts, okay, which means that we have different types of teeth. The structure is according to the function, all right, form follows function. Just like fish have homodonts, they all have little cones for teeth because they don't chew with their teeth. They just basically tear and swallow, all right? But we know we have molars, we have premolars, we have canines and scissors, and we have different types of teeth for doing different things to the food that we eat. And the molars are there for a reason, which is to grind. And so one telltale of chewing the food well is that when it comes out, it doesn't look the same shape that when it came in. And that applies particularly to corn. And so it comes down again to human behavior. Chew your food well before you send it down, really grind it down to a pulp. And so a lot of it is habits. It's feeding habits, eating well, eating slowly, don't rush it. And that does much more for digestion than the different types of food that we actually eat. It's just chewing it very, very well before we gulp it down. Anyway, that was my 2 cents on digestion. Let's move forward to another energy source, still on the biofuels, biomass. Actually wood. Wood is also another 1/5, and wood is being used for burning, again, to heat up water and to generate steam, to run the turbine, to turn the turbine, and the turning of the turbine will generate electricity, which is pumped out into the grid, okay? So just wood chip or old furniture and stuff is ground up and burned. But the downside of this, of course, is that it does produce CO2, which has to be filtered and so forth with the active charcoal. And also the burnt wood produces ash, which is then mixed with soil to make potash, and then that potash can be laid out on the ground for fertilizing the ground and so forth, because that's essentially carbon that can be sunk, this ash when it's mixed with soil, and then the rain pushes it down into the soil, into the ground, into the rock. So this part of the carbon can be sunk in, right? But the offender, of course, is the CO2 that is produced in the burning, which needs to be trapped by filters and so forth. But anyway, I'm just pointing out the fact that of the renewables, about 1/5 of it comes from just burning wood chips. Okay, let's move forward. Different concept altogether, wind. So anything that is moving through the earth, any fluid, we talked about the fluid of water for hydroelectric. Now we can talk about another fluid, which is the wind, is the air moving, can move helices, what's another word for a helix? And generate electricity also, all right? Very clean. It's almost 1/5 of it by wind power. You see these windmills along the way. You see them a little less in the US. I see them more in Europe, in part because Europe generally has a more accidented terrain, and the accidented terrain makes for more wind tunnels and rushing of wind in between mountain ranges and so forth. And so they're able to take advantage of that, of those natural wind tunnels in Europe more than us. But in general, also because in Europe, in general, they're paying about 4 times more than we pay for gasoline here, okay? For example, we pay whatever for a gallon of gas. Let's say we pay $2 per gallon for gas. They'll pay $2 or 2 euros, which is almost the dollar. It's almost to the euro now, per liter, under 4 liters in a gallon. Okay, so they pay about 4 times more for gasoline, and therefore they have much more emphasis on alternative energy resources in Europe, big time, even by legislation, by the way. Okay, so these are the windmills, the typical ones that we see, but there's another style also. So this one moves vertically, the helix moves vertically, but there's another style also that is out there. It's not as common, these other helices that move horizontally. And the one advantage of these is that they can pick up wind from any pattern. If the wind changes back and forth, which again happens in Europe a little more often than here, the wind pattern tends to change back and forth. So these horizontal helices, you know, they turn on their edge, on their axis, can pick up wind from any direction. Whereas these vertical ones are more unidirectional, that the wind pattern needs to come in a common direction. Anyway, this is a very clean energy source. Some downsides is, well, the first one is they're just unsightly to some people. They consider them an eyesore, literally. Look at the scale, okay? These are trucks on the road. So look at the scale. A human would be down here, so they can be seen for quite a distance. Typically, they're in this color, white and so forth. So sometimes they blend in, but they can also be an eyesore on a natural landscape. That's one negative. Another negative is that sometimes flocks of birds do get to hit these things. For some reason, they don't see them, or they don't see them fast enough to, I mean, many flocks do avoid them, but some birds get killed by these helices, all right? Even though they don't turn very fast, you actually see them turning. They don't really turn that fast. To generate electricity, they don't need to be spinning, you know, like a propeller. That's the word I was looking for. Like a propeller of a plane, where you actually don't see the asps. You don't see the individual propellers when a propeller is turning on a plane, all right? But these, you actually see them rotate. They rotate rather slowly because that's enough to generate the electricity that is needed. All right, so anyway, wind, almost 1/5 of it. It'd be nice if this could be increased. A way of increasing this is simply by putting more of these out there in the landscape, all right? But they're gonna be eyesores for some people.
Where are these used, Father? Where are these pictures taken, do you know?
No, I don't know. I'm sorry, I don't know where this is taken. It's obviously a very flat area, okay? It seems like some kind of a landfill. This seems very unique here, very, not unique, very homogeneous to be a natural landscape. So it's probably some kind of landfill along a lake, or it could be the ocean. I'm not sure. But there are many, many of these images. You can Google them and you'll see them all over the place. Again, like I say, a lot in Europe. You see these, I've seen them just driving around. All right, another source, just burning trash, essentially, burning trash, okay? Good old trash, which is what's going on right now. I understand that the recycling is not working too well. I'll get back to that comment in a minute about, at least in Miami-Dade County. But this is what the big garbage trucks are doing. They're taking the trash. If they don't take it to a landfill, they'll take it to a station where the trash is burned, again, to produce heat, to produce steam. And the steam will run the turbine, and the turbine will generate electricity. The electricity is pumped into the grid, all right? In the process, CO2 is produced, much larger amount of CO2 than just wood chips, of course, because this is all kinds of trash. And that CO2 and other toxic gases are put through filtering systems, more elaborate, complex filtering systems, so that what comes out is regulated, again, by EPA, the Environmental Protection Agency that we have in place in the United States, assuming that they're not corrupt, they're doing their job, which is that they're patrolling, they're policing these stations, these garbage burning stations, so that their filters are in place and they're changed regularly, and they take samples periodically of the stuff, and if the stuff is coming out dirty, they'll shut down the station until they get their act together and clean up the filters and replace them and so forth, because we have environmental regulation in this country that hopefully works. And the affluent then has to be clean air, you know, and air that is breathable. And again, you see a lot of these stacks are putting out smoke, but the smoke that is coming out is water vapor. Okay, it's water vapor, so it's not CO2. Again, the ash is taken to a landfill, can be mixed with soil to make potash, and then that soil can be used also for farming, etc. Can be sunk back into the ground when it's allowed for rain to go through it and pick up the carbon and sink it into the soil. All right. So the comment that I wanted to make with regards to recycling, this is very disappointing to me because I take a big effort to recycle everything that can be recycled into the commingled bins. And you saw that little video last lecture of the commingled bin, right? We started out, I remember, back, I guess in the 80s or 90s here in Miami, where we had the 3 types of bins for paper products, and then for glass, and then for metal cans, and then the 4th bin for plastic. And we were just too lazy to do that separation, okay? And it was getting contaminated. So if the plastic bin had just a single glass bottle, or if the metal bin had a single plastic bottle, that contaminated the whole bin. And so that whole bin had to be thrown out, could not be recycled. And so because of essentially of our laziness in the human nature and human behavior, it pushed the industry to go to this commingled, meaning that it's a single trash bin, those big, huge green bins that we see around the city, right? So now we can put everything that's recyclable in there. The 4 different things, the plastics, the metals, the paper, and the glass. All right. But now I hear that that industry, because it keeps getting contaminated, the bin gets contaminated with soiled garbage. Mm-hmm. And so the industry cannot afford the manpower to separate the recyclable material back in the station, to separate the recyclable material from the contaminated trash that we individuals threw in that bin, that recyclable bin. So the whole bin has to be thrown out. The bottom line is that because of our wages, etc., the industry now cannot make it profitable to recycle the material that is in those green bins. And my understanding is that very hush-hush, all the recycling material that we're producing in the city and that we're carefully putting in those bins, or not carefully, is ending up in a trash heap together with the rest of the garbage, and eventually burnt up or in huge landfills, okay? So again, it comes back to the human behavior. The industry is what it is, and we can regulate it to the hilt. But if we over-regulate industry, they'll shut it down because they can't afford it. It cannot be. And also because we're used to these high wages. If people would settle for a little lower wages to do the manual work of separating the trash, the contaminated bins from the real recyclable material, then perhaps, but no. All these workforces, typically they're unionized, and so the syndicates are very strong, and it goes back into the commerce and into the politics and into the economics of it. It's the complex reality of a mixed economy, And
Father, even with the recyclable materials, if humans don't clean it, it's going to be contaminated and it's going to be discarded regardless. I mean, if you get a gallon of milk and you're done with your milk, you just need to rinse the milk off, because the moment they see any residue of something that was once upon a time alive, it's no longer useful.
Right, there you go. Okay, and so how many of us are actually cleaning that water bottle or the milk gallon, the milk bottle and rain? Yeah, and then the next, what the next thing is going to be? Oh, by the way, we want it dry also. Okay, because
I dry them as well. I mean, because I know I don't want it to be discarded,
and that's where
I know for a fact that there's no such thing as a safe landfill. So I rather it be done right. At least absolutely. I do.
It's just more work. It's discipline. It pays off, and Europe is going that route. And their ideal is actually that each household will have zero output of waste. Okay, that's the ideal.
Father, you went back and you said, you indicated that some of the costs are because we're paying people higher wages, and you got a little aside there about unionization. We could also pay higher taxes. It's sort of like paying, like at McDonald's, if you want to pay extra, so we're not living tomato farmers up in Immokalee basically live on poverty wages. I mean, that is a really—
I agree. Again,
okay, that's not how you said it.
Yeah, I keep using Europe as an example, because in Europe, they do pay higher taxes. They pay 20, 30, 40, and 50% tax, okay? And it's called virtuosity. That's the standard now. It's very interesting to me. I find it kind of ironic that Europe is kind of going full circle on virtuosity, because it started back millennia ago with virtuous ethics, the virtuous living, all right? And people would strive, civilized people would strive for living a virtuous life, the virtues, living the virtues.
Right,
okay?
But Father, you actually had a more,
please.
economic.
Look, unfortunately, I keep getting interrupted in my thoughts, so I ask respectfully to let me finish what I'm teaching, okay? Thank you. So, virtues now, it turns out that Europe now has a system of compensating and of rewarding virtuous state, and the states actually seek to be virtuous, but it's quantified, it's measured. And one ideal, for example, would be what percentage of one standard, what percentage of the town, of the city, or the population actually has zero waste output, all right? That everything is recyclable locally. So I buy stuff and then I recycle it myself at home in many different ways, so that I really have no garbage. to put out, okay? And that would be like the highest standard, the ideal standard of virtue. And then they quantify that, what percentage of the population is doing it, and they add up all the percentages from the different cities. And one way or another, they come up with a national percentage of virtuosity, and then that gives them like tax breaks, or they have other incentives. They have economic incentives at the European Union level, at the level of the European Union, okay? And so I just find it interesting that now virtuosity basically is being quantified by this being very conscious, ecologically conscious, all right? At the level, and they're bringing it down to where the ultimate culprit is the consumer, right? Because if we didn't consume the product, the industry wouldn't produce it. It's supply and demand. If there was no demand for the supply would dry out. So because we keep demanding the product, it's being supplied, all right? And so we have to understand those basic things about economy. But again, just to note that I find it interesting and encouraging, actually, that the language of virtue is being reintroduced in Europe after undergoing a huge and horrible secularization for decades now, you know, of devaluing many of the values that we hold dear, at least in Catholicism and Christianity. And yet it's coming back to them by way of ecological conscience, all right? Okay, let me move forward, please, because we still have quite a bit of ground to cover here. I want to look at solar. And solar right now in the US, it's only about 5%. I find it very, very promising. One downside from the get-go is that it's still rather expensive because it involves more or less high tech. I just want to mention briefly that we have basically two options right now for solar. What I mean by solar is using sunlight to generate electricity, okay? Basically, that's the conversion from solar energy to electrical energy. And the electricity can again be pumped into the grid. So the solar panels, which are known as photovoltaic cells, and these photovoltaic cells, what they do is they do an energy transformation. They take light, they take photo or light, and they transform it mostly by silica plates that transform some of the light into electricity, okay? Little tiny bursts of electricity that are then gathered by each one of the panels, each one of the cells in the panel, and each panel contributes a little bit of electricity. And when you put a massive amount of them, like a farm, a solar panel farm, then you eventually get a massive amount of electricity that can be fed into the electrical grid, okay? So this is one style, one option, one technology, which is a photovoltaic cell. And while it's still on this one, it has been brought down to the home level also. So you have solar panels that can be installed on rooftops. We actually have one little house here. It's just a model one-room house. We call it the greenhouse because it's painted green, not because it's a glass house. But it has a solar panel roof, all right, that is generating electricity all the time. And inside that little house, we have actually batteries where we store the electricity, and then that electricity is used to run the organic garden next door, the water pump that we have, and also the chicky hot. So eventually, when God willing, you'll be able to come back into campus, you can look at the little greenhouse on the left next to the forest with its solar panel roof, all right? And so creative design can do the roofing, can also do the garage, the driveway, and so forth. Any surface that is exposed to sunlight can be solarized, can be, panels can be put there. In fact, some people have gotten very creative and have designed solar panels, photovoltaic cells that look like tiles. And this is an example, these actual photographs of different styles of tiles that can be used on the roof tiles, all right? The barrel tile that we have here in South Florida, or shale or slate tiles that can be found in the north. These are different styles of roof tiles that are actually photovoltaic cells. All right, I think it was Elon Musk, the guy who also did the Tesla and the other thing up in the sky. What is that called? Virgin Atlantic or whatever. So some people have gotten very, very creative in trying to commercialize photovoltaic cells. And I hear that even newer generations of photovoltaic cells are transparent and flexible. So even just a glass panel on the window can be a photovoltaic cell, all right? Because the filaments are now microscopic and cannot be seen by the naked eye. And so glass panel, even that is flexible, like a plexiglass, can also be a photovoltaic cell. Very, very creative, right? A different method, a different technology is what is known as concentrated solar power, or CSP. It's not as popular as the photovoltaic cells. One reason is it takes more space, but also the technology is totally different. So let's look at this photograph for a moment. What you see here, all these panels are not photovoltaic cells. They're not solar panels, okay? These are not solar panels. These are actually mirrors. These are all mirrors, and that's why you see them arrayed in this different pattern that you see. It's kind of an interesting pattern. It actually follows the rotation of the sun from sunrise to sunset, different times of the year. But you see there's an interesting pattern of array of these mirrors. But all of these mirrors, what they're doing is they're reflecting sunlight to this big bulb up here on top of this tower. So you see the tower at the center here, and this bulb, which is white. This is literally white hot, okay? Like the core of the earth, this is white hot. In other words, it has gone beyond red hot. It's like a humongous filament. Remember the incandescent lights that I'll talk about in a minute further down, all right? They get white hot. So what it's doing is all of these mirrors are reflecting the light, concentrating it on this huge bulb here that turns white hot, and some of that heat is transmitted down. The heat is transmitted down into this area where water is heated up into steam, and then a steam engine is run, okay? So a turbine is run by steam, and the steam is generated by the hot water that is generated by the heat that is transmitted down from this bulb, this white hot bulb, okay? And again, to get a feel of the scale, you see this little thing here, that's a truck. These other things are trucks, all right? And so to get a feel for the scale, maybe these two little dots here are two humans, I don't know, but this is a huge structure. And that's why it's not that popular. It has to be that large in order for it to generate enough heat to make it, again, cost effective, to generate the electricity cheaply enough that is cost effective, okay, for the whole setup. I understand that we have at least one of these somewhere in Central Florida, and guess what? Who's running it? FPL, all right? And or some subsidiary of FPL. Maybe they have a branch that is the research branch. But yeah, this is another innovative way of taking just light from the sun and channeling it, transforming it eventually into producing electricity that is totally clean, you know? And so even though that's another reason why this bulb has to be so high up, because it turns white hot and it generates heat. But this heat then dissipates, and of course, at nightfall, this goes dark, right? Okay, so the creative idea. Moving forward, geothermal, we're down to 2% of the 10% of renewable energy produced in the US. Geothermal is tapping into that core and into that mantle, which is very hot, all right? And when we tap into that mantle, we're going to get some heat that will heat up water, and that water will be turned into steam. And again, the same old machinery, the steam will turn the turbine, and the turbine will generate electricity that will be pumped into the grid, all right, for running industry and everything else. So that hot water then eventually needs to be cooled down, and this could be one of those towers that you see cooling the water, and that cooled water then is injected back into the groundwater and so forth. So there's a recycling here, and the renewable source essentially is water. Water that is hot water, the steam used for generating electricity, cooled down over time, and then pumped back into the soil or into the water table, okay? So geothermal, and this is a photograph of a geothermal plant. Again, all the steam that you see out here, all the white smoke, is not CO2. There's no CO2 produced here, all right? So this is clean from that perspective. This is just water vapor. Moving forward. All right, another graph just to show where we're at more or less right now in the 2000s of consumption power. So we have, starting from the top down, still coal is the major producer, the major source for producing kilowatts, for producing energy, electricity in the US. Still coal is the major one by volume, trailed by nuclear. And then the renewables are down here in general. And the other fossil fuel is petroleum, which is, sorry, where am I? I lost, sorry, natural gas. All right, first the fossil fuels, coal, natural gas, and petroleum way down here, okay? It's too expensive to run in industry anymore. So these are the two cheapest ones still. Then, this is nuclear, which is kind of leveled off. And finally, renewables. But what I find interesting, at least, or encouraging, is in the slopes of these curves. If we look at the last decade or so, since the millennium, the new millennium, coal is definitely a negative slope. Nice large negative slope, which is a good thing, right? Much less CO2 on its way. Petroleum is way down here anyway, so it's not that significant. Natural gas is increasing here, it has a positive slope. So for now, natural gas, we have to live with it. Again, if we control through the EPA the emission of this natural gas, then we can make it clean. Nuclear is leveled off, but again, the encouraging thing is the renewable energy. You see a nice little spike more recently here. So this has potential for picking up moving forward, especially if we put more technology into it. And as that technology becomes more cheaper, essentially more economic, the industry will be more attracted. So what I find encouraging is in the slope of this one, which is a positive slope, and the slope of this offender, which is a negative slope. All right. Okay, how about we take a break now? Because from now forward, I'm just going to get into some alternative energy sources at the consumption level, what we can do as consumers, right, to be more ecological, to be more eco-friendly in using alternative sources of living for our daily living. So I think this is a good time to break. Also been going on for over 2 hours now. So unless there's any question or comment at this point overall. Anything? No? Okay, let's take a break. I have 11:45, so how about 10 minutes, okay? I'll start again at 11:55 so that we don't go too far. All right, so let me pause this recording. Okay, so welcome back. What I want to do now in the second half is show you some creative ways in which industry really and commerce is trying to supply our demand for these energy sources so that they are more clean and eco-friendly, if you will. So let's move here to the next slide. For example, in the oceans, there are two systems that are being tried out in the ocean. One is to catch the motion of waves. So anything that's moving potentially could generate electricity by way of the motion itself, all right? So here we have this long worm. It's a metallic worm that bends with the wave as the wave goes along it, right? It bends up and down, back and forth, and in that motion, it generates electricity. So that's one system that is totally clean, passive, it's just using the motion of waves through the ocean. Another one is when that wave hits the shore, is these two buoys basically move up and down, all right? And you can see there are different levels here. They move up and down just simply passively from the wave, and that motion, up and down motion here, also generates electricity because they get plates to move against each other to generate electricity. The electric car, little did I know, this is a fully electric car, not hybrid, because with hybrids, what you have is some electric motor. You have an electric motor, but you also have a gasoline motor. And there are different types of of hybrid cars. Some that are, let's say, from one extreme to the other. One extreme is that they run mostly on gasoline, and they use the electricity as a backup. And the other extreme is that they run mostly on the electricity, but then they use up gasoline as a backup. Those are the hybrids, okay? But with the hybrids, at the end of the day, you end up with two motors. You end up with an electric motor and a gasoline motor, even if it's just a generator to generate the electricity. Of course, you get very good mileage on them, 200-300 miles per gallon, whatever, because it's running partly on the electricity, okay? But here, that's not the kind of car I'm talking about. I'm talking about a fully electric car. They're known as EV, electric vehicles, right? Full electric car, there is no gasoline. Now, no gasoline implies a lot of things. There's no pistons, there's no gasoline motor, so there's no combustion, there's no piston. If there's no combustion, there's no CO2 emission, all right? And also the parts that don't exist in an electric car, because there's no pistons, there's no gasoline motor, there's no oil change, for example. There's no transmission either, because they have what is known as direct drive. You step on the accelerator and the car moves faster and faster, okay? It's direct, the electricity goes directly from the battery, which is underneath the chassis of the car, directly to the electrical motor. So there's no gas tank, there's no gas pump, there's no starter motor, there's no radiator to cool down the water that cools the motor, or the oil that cools the motor. So many parts of a gasoline car don't exist in an electric car. Electric car is much more simple. Basically, it has structurally, mechanically, has a huge battery underneath, very flat, underneath the chassis, which, by the way, makes the car very bottom heavy, right? The center of gravity is at the bottom of the car, so it's extremely stable. Turning the quarter barely tilts at all, turning a curve, because it's very bottom heavy. All the weight is at the bottom, most of the weight. So it has this battery underneath, then an electrical motor to run the tires, typically front traction, front tire traction, and the converter of the electricity from the battery to the motor itself. So it's very simple mechanically. Very few parts can actually break. There are very few moving parts in it, much fewer than a gasoline car, all right? So that's an electric car. And I happen to have one of these. Little did I know when I first put this presentation together about 6 years ago that I would end up with an electric car that is precisely this model. This is a Leaf from Nissan. It's one of the first electric cars that was available in the market. I bought mine used, but it only cost me $8,000. It's a whole car, that's it. And it's 5 years old now, so the technology is old. It only has about 80 miles on the range, on a full charge. So these cars are urban cars. In other words, they're for running around in the city. Typically, you use it during the day, and then when you get home, you plug it in overnight. You plug it into a regular outlet, 110-volt outlet on the wall, plug it in, and recharge it overnight, and then run around the next day, the same thing. They're not really meant for long travel yet, but like I say, my model is an old one. It's 5 years old, so the range is about 80 miles. The new models now are between 250, 300 miles on a charge, okay? My brother and sister-in-law just leased one from this year, and it has about a 300-mile range on it. So the technology is increasing very fast on these. And I find it very, very encouraging and hopeful because these are totally clean. I mean, you could keep this in the middle of your living room if you want it. It's very silent, very clean, doesn't smell like anything, and cool also, particularly for our subtropical weather, since it doesn't have that gasoline motor that puts out a lot of heat. Then the air conditioning is extremely efficient. It also has an efficient braking system that is called regenerative braking. In other words, once I take my foot off the pedal of the accelerator, the electrical motor turns into a generator and it starts recharging the battery. Of course, it doesn't recharge fully because there's always friction that is lost. But the best thing about that I find is that the car starts slowing down. It's braking passively without using the brakes. So the brake pads will last years and years because I seldom use the brakes. When I see the red light or the stop sign, I take off the foot from the accelerator and the car is naturally, automatically decelerating because of the generator that is generating electricity back into the battery. Okay, so it's a very exciting new technology that is extremely clean. Much cheaper, the rate per electricity. So you can say, well, what's the downfall? The downfall is two. Number one, for now, the range, even though more and more stations are appearing on the road and in different places, public stations where one can charge. Also, many universities and other buildings now have charging stations for electrical cars, EVs. You have to swipe your credit card, of course, because they're not going to give you the electricity for free. But at the end of the day, it's estimated, my estimation is between $200 and $300 a year of electricity at the current rate of FPL wattage, kilowatt per hour. It comes to about $200 to $300 of electricity per year. So you tell me how that compares with your gasoline bill, your gas bill, all right? And I can tell you that in 5 years, I have not been to a gas station, not even to change the oil change because there's no oil to be changed, all right? So totally maintenance free. I take it back to the agency once a year and they say, what do you want? There's nothing to be done, it's maintenance free. Just keep recharging it and keep driving it. So yeah, the downside is also the battery that may last, I don't know, maybe 8 to 10 years, and eventually the battery will wear out, got to replace it. And they estimate $2,000 to $3,000 to replace the battery. But in 10 years' time, one has certainly gotten its money worth out of it. And by now, in 10 years' time, the technology will be much more advanced. The batteries will be better, et cetera, et cetera. So I'm very hopeful for the EVs, for electrical cars, all right, to replace gasoline cars and diesel cars, which are the major polluters, one of the major polluters on the road in the US and throughout the world. Okay, another one is what we've done with light bulbs. This is, at the residential level, at the home level, at the level of the 320 million that we are in the United States, that at night we like to have light in our homes. And so we've gone from the incandescent bulb, which was that white hot filament that used up a lot of energy, to the fluorescent bulb, right, which was gas, neon gas, or some kind of gas in here that became iridescent and gave off light, to now to the LED, light emitting electrode, diode. So LED is an acronym. It means light emitting diode. The light emitting diode. Oh, here it is down here. All right. This is the latest craze, and it's much more efficient. For example, an equivalent lumen of light. Here's lumens. Lumens is a measurement of light output, actual brightness. Okay. 840 for a 60-watt bulb of incandescent light is equivalent to 18 watt of fluorescent bulb, and it's equivalent to 10 watts of an LED bulb. So much more efficient, 6 times more efficient than an incandescent bulb, okay, the LEDs. They last much longer, 1 year compared to more than 20 years for an LED, all right? So they're 6 times more efficient insofar as usage of wattage, of watts, which is the power of electricity that has been used. They last 20 times longer, approximately, more than 20 times. Of course, they cost more initial investment, about 6 times more, again, because what's ruling the price here is the wattage, right? So $2 for an incandescent bulb, $12 for an LED bulb that uses 1/6 of the electricity. So it's 6 times more expensive, right? You follow the economics? It's very straightforward. But when you average that to 20 years instead of 1 year, you end up paying less than $2 per energy cost as compared to more than $7 energy cost on the original incandescents, okay? And fluorescent is somewhere in the middle, but it comes down more expensive fluorescent than LED. So basically, LED is the latest out there for light, and it is a light emitting diode, which by the consumption, when we do the math on the annual budget, it comes out much cheaper. So what I'm trying to say by this is I highly encourage you to change all the light bulbs in your home to LEDs, all right? Whether they're fluorescent or incandescent, you have an initial investment of more money, but they'll last you much longer, and you'll be saving by next electric bill, you'll be saving lots of energy by going to LED, all right? Okay, you find them all shapes and sizes. These are designed so that they fit into the sockets for a regular light bulb and all other different designs that you can find. There's also strips of LEDs that you can put along the wall, etc. You can get very creative with LED lighting. I also want to mention this, for example, for the future, you look at this rail here. This rail is a magnetic rail. It's a train that is magnetic, okay? So it's traveling actually on top of a huge magnet. And if you can look here at a close-up of this area, you see that it's actually floating. It's actually floating, all right? Just like when you bring 2 magnets together by the same polarity, positive to positive, you see how they tend to repel each other, all right? So these have the same charge. Let's say that the rail itself has a positive charge and the train also has a positive charge underneath that can be generated electrically, right? An electromagnetic charge. And so positive to positive will repel. The end result of this is not only is it a clean run, literally, because it's not burning anything, not emitting CO2 at all, but actually there's no friction. So it moves much faster. And these are those high velocity, what is it called, TGVs, trains that again are beginning to exist in Europe now. The train de grande vitesse of high velocity, because there's no friction, all right? There's air in between the actual train and the rail. So this is very exciting technology. Again, today it's still somewhat expensive, like this guy, but in the long run, much cleaner and faster transportation. This would be for public transportation. Let me show you these two videos talking about creativity, because here is electricity generated from green plants and also electricity generated from algae or biofuel, which can be turned into electricity from algae. All right, so I have the videos here, hopefully. What I did is I loaded them beforehand. So let me go to change here to the optimize share for video screen. Okay, hopefully, well, let me do this. Yep, and now here, go to the start.
Electricity. In a small way, they already are in research laboratories and greenhouses at Project Plant E, a university and commercially sponsored research group.
Bring it to the start. Bear with me. Also full screen. Okay. Hopefully it will not be blurry. If it's blurry, then you always have the link there that you can watch. Here we go.
Plants like these could soon provide our electricity. In a small way, they already are in research laboratories and greenhouses at Project Plant E, a university and commercially sponsored research group at Wageningen University in the Netherlands. It's called the plant microbial fuel cell and can generate electricity from the natural interaction between plant roots and soil bacteria. It works by taking advantage of the up to 70% of organic material produced via photosynthesis that can't be used by the plant and is excreted through the roots. As naturally occurring bacteria around the roots break down this organic residue, electrons are released as a waste product. An electrode absorbs them and generates electricity.
Zonnepanelen maken meer elektriciteit op een...
Solar panels are making more energy per square meter, but we expect to reduce the costs of our system technology in the future. And our system can be used for different applications.
Verschillende toepassingen op hetzelfde oppervlak kunnen combineren.
Plant microbial fuel cells can be used on various scales. An experimental 15 square meter model can produce enough electricity to power a computer notebook. Our system can be used for different applications. Our technology is making electricity, but also could be used as roof insulation or as a water collector. On a bigger scale, it's possible to produce rice and electricity at the same time, and in that way to combine food and energy production.
En als we op een gegeven moment echt grootschalig deze technologie gaan toepassen, dan kunnen we bijvoorbeeld ook op hetzelfde oppervlak rijst produceren en elektriciteit.
A first prototype of a green electricity roof was installed on one building at Wageningen University, and researchers are keeping a close eye on what's growing there.
Okay, so that's one example of creativity where plant metabolism is...
The two most common reasons people go to see plastic surgeons are
plant material is being used for generating electricity. Okay, here's another one that is growing algae as an alternative, a crop source to the traditional crops that we grow in the fields. Again, let me bring it to start. And here we go. Okay, so that's one example of creativity where plant metabolism is being used for generating electricity. Okay, here's another one that is growing algae as an alternative, a crop source to the traditional crops that we grow in the fields. Again, let me bring it to start. And here we go. Okay, Magnify the screen. Here we go.
Iowa, where corn is almost a religion. A new faith may be taking root.
This is algae growing out of solution. It looks just like a cornfield. We run the harvester. This harvester reminds us of a combine pulling off the algae.
Algae? Isn't that something we usually try to get rid of?
You can actually crack the code on actually growing and harvesting algae and getting this biomass. The applications for this biomass is really incredible. You can use it to feed animals, you can use it to feed people, you can take its very high value in proteins. You can use it to fuel your cars, you can get the oil out of that. So when you look at algae, that's why so much interest is in it, because it has such a wide application in so many different sources.
In addition to its biofuel possibilities, algae is already being used in all kinds of ways you might not be aware of. Food products, baby formula, or nutritional supplements like spirulina. Algae contains the all-important nutrient omega-3 fatty acids.
It's all about omega-3s, and the world is short omega-3s. They're long omega-6s and omega-7s, but they're short omega-3s, and algae may have the best ability to solve the shortage of omega-3s in the world at the highest quantity.
Quantity, that's what they're trying to tackle here in Shenandoah, Iowa. In an unusual pairing, a traditional corn ethanol plant is supporting algae production, a next-generation biofuel. It turns out corn has what algae needs.
A third of the kernel is starch being converted into fuel, a third of the kernel is fiber being converted into animal feed, and there's a third left. And all that is being converted into CO2 in the atmosphere. So we could actually take that other third of the kernel that we're basically emitting into the atmosphere, capture it, and create a whole nother product around how we convert CO2, warm water, waste heat, and sunlight into algae.
CO2, wastewater, and heat, all byproducts of producing corn ethanol, exactly what algae needs. And this joint project called Bioprocess Algae is the result of an unlikely partnership.
This whole process has been serendipitous.
Todd Becker, CEO of Green Plains Renewable Energy, a major producer of corn ethanol, and Tim Burns, CEO of Bioprocess H2O, a water treatment company whose technology has been used to get algae out of water.
How to keep algae out of wastewater systems. We have a lot of knowledge, and that knowledge gave us the opportunity to bring it into how we can grow algae, and we knew that with our system. The heart of it is attached growth. We have a system in which we provide a lot of surface area for the algae. Basically, think of a condominium for the algae to reside on. And that condominium provides a lot of surface area, so we have a big mass transfer device. Think of it that way. So on a typical open pond system, which algae is traditionally grown on, we would be about 40 times the surface area of the system. So it gives us a lot of opportunity to be more cost effective.
Let's say an acre of land. An acre of land that produces corn today in the United States produces 7 tons per acre. Our goal in these reactors is to get 15 to 40 tons per acre of product.
And instead of a once-a-year harvest, algae is harvested several times a week. The idea of getting gas and oil from algae is really not new. In fact, it's millions of years old.
All our oil today is ancient algae deposits, compaction of hundreds of millions of years of riverbeds and compaction of algae already. What we're trying to do is accelerate with the process and to what Mother Nature has done so effectively and start to industrialize it and produce by our process. The stumbling block is cost.
But recent breakthroughs promise to reduce that cost. At the Pacific Northwest National Laboratory, researchers have developed a technology that uses extreme pressure and high temperatures to accomplish in minutes what nature has done over millions of years: convert algae into oil. Still, to be cost-effective, algae needs to be grown in high volume, and co-locating algae production with a corn ethanol plant might point the way.
You basically can use free inputs, the sunlight, wastewater, warm water, heat, and CO2, and there's a lot of all of that available. And so if you actually combine all that, you actually take something that is really free and you're going to create something with a lot of value.
And in the process, they just might be teaching the rest of the world a new way to look at that greenhouse gas, CO2. Instead of a pollutant, it could become a product.
If you think about the ability to utilize greenhouse gases and CO2, algae, in my opinion, is the only profitable use of CO2 currently on the market. So if you're able to profitably use that CO2 portion, that's going to give you opportunity to mitigate the rest of the CO2 emission.
Reducing CO2 emissions while growing a renewable and sustainable fuel source that could mean less expensive gas. That is the promise of algae. It may be a while before algae dethrones corn in this part of the world, but as this remarkable experiment is demonstrating, there's no reason they can't get along.
Okay, I understand that perhaps some of you did not see the video. You heard it but didn't see it, or the image was frozen. So again, I apologize for this. I really don't know what's happening there, but at least the good news is that you have here the two links, okay? They're short videos, like 2 minutes, 3 minutes, and the other one's a little longer, 5 minutes. But watch them on your own, please. All right, take a look. This is very encouraging, innovative, creative ideas that are coming out, thinking out of the box, as it were, to try to make it feasible. Of course, we understand that it has to be that it has to be commerciable, right? That it can be sold, as it were, to industry and to commerce, so that it will be feasible. Otherwise, if it's too expensive to make, it's not going to survive the market economy. All right, I did want to talk a little bit about hydrogen fuel cells, because this has been coming up more recently, even as recently as a couple of weeks ago. You may have seen the news of a tractor now running on hydrogen fuel cells, which is an alternative, let's say, to the electrical battery, all right, for transportation. It's an idea that's not really new in itself. It's been around for some time, but again, it's not yet cost effective. Just a little bit on the basics of how this happens. Essentially a membrane that takes oxygen from the atmosphere and takes hydrogen from a source, right? Because there's very little hydrogen in the atmosphere, remember? It's a very, very tiny percentage because it's so flammable that our atmosphere would be unsafe if it were any higher. So this hydrogen has to be manufactured for this machine to work properly. Anyway, let's bracket that for a moment. The fact is that by taking water, gas, by taking oxygen gas and mixing it with hydrogen gas, we generate water. We generate water through a membrane, all right? And in the generation of that water, electricity is produced. It's produced if we have two metal plates next to the membrane. The oxygen and the hydrogen are flowing through the membrane, and what comes out of that reaction is water, and electricity is produced in the process. So the two metal plates that are to each side of the membrane, they pick up electricity that can be sent to a collector of electricity, essentially put through a voltage converter and charge a battery. That battery can then be used to run a motor or put it in the grid, but the more efficient way would be to actually use it to run a motor, all right? And so this is the hydrogen fuel cell that would be used. So hypothetically for the car, and there are already some cars that have the hydrogen fuel technology, is an alternative to the just straight up EV just battery that needs to be recharged. The tank, the hydrogen tank, would be in the back of the car, equivalent to the gas tank, where the gas tank is today, but they're actual gas cylinders, they're hydrogen cylinders. Then the fuel cell, where this process occurs of producing water, and the water then is the byproduct, which is eliminated onto the ground underneath the car, just pure water, all right? And the electricity is made this way, which will be used to run the motor of the car, the electric motor for moving the car, propelling the car forward. That's the basic theory behind it. Like I say, some experimental cars have been made already, and some were put in the market actually a few years ago. But there's a downside, and the downside that I mentioned, there's very little hydrogen in the atmosphere, and it's too expensive to pull out. So hydrogen actually has to be made. Hydrogen gas has to be manufactured. And the manufacturing of hydrogen gas now is expensive, all right? It has to be manufactured and then pumped into the gas cylinder, similar to pumping gasoline into a car, all right? But the station has to have hydrogen tanks and the pumping station. And so we see that the price here is the rendimiento, the amount of kilowatt hours that we get per liter of hydrogen is much less than gasoline or diesel, all right? The scale here on the y-axis, the vertical axis, is kilowatt hours per liter. These are the units. So think about this for a moment. Kilowatt hours, all right? In other words, how many kilowatts per hour are being pumped out per liter of these different substances, okay? And of course, the higher the kilowatt per liter, then the cheaper it is per unit for running whatever vehicle we're going to run. So hydrogen is at the lower end, less than 1 kilowatt hour per liter. In other words, for 1 liter of hydrogen gas, right, we get less than 1 kilowatt of electricity per hour. That's how to interpret this. On the opposite end of the scale, the two largest ones, the two most effective ones are still gasoline and diesel, because with gasoline and diesel, we get more than 8, we get around 9 or 10 kilowatts per hour per liter of gasoline or diesel, okay? So about 10 times more. We get about 10 times more energy, more electricity out of gasoline per liter than we get out of hydrogen. And that's why it's still not that cost effective, at least at the level of the individual car, When we get into mass transportation, when we get into public transportation of several people, dozens of people benefiting from the same motor, okay? Or when we get into heavy industry, then it is more cost effective, to the point that there are already hydrogen buses, like this 2-decker, the double-deckers that are typical in London and in Great Britain, right? And some double-deckers here that are used mostly for tourism. Of course, for the same basic motor, you get to transport more people, all right? The same with trains. So this is a hydrogen double-decker that is already commercial and is being produced and sold and bought by different cities of the world. And also, this is a hydrogen subway, light rail, all right, above ground rail, that is also running on hydrogen. There's also an airplane now that has been manufactured that runs on hydrogen, okay? And also heavy equipment construction. This is excavator the construction material or heavy industrial material, machinery can be moved. So what happening with hydrogen then, it may not replace the electric car, the technology, because at the level of the individual car is too expensive. In other words, we don't all have at home, you know, a hydrogen producing machine. Is too expensive. But when you get to the level of industry in large places, in large, like the bus station, for example, there could be a hydrogen producing plant that pays off because it makes hydrogen in larger bulk quantity to gas up all of their buses or the train, or to gas up heavy equipment, machinery, all right? So when it's used in large scale, then it does pay up to use hydrogen, but not at the small scale of individual cars. So it could be then that in the future, moving forward into the future, cost-wise, cost-effectiveness may be that at the level of individual transportation or family transportation, single family, the electrical vehicle will be the best one. But at the level of public transportation or heavy machinery and even flight, hydrogen fuel may be the best one overall, okay? Anyway, these are creative ideas moving into the future, are beginning to happen already. These are actual photographs of equipment that is already out there in the, available for buying and selling. Okay, as far as home is concerned, also we can take advantage of a number of things that are alternative energy sources that don't use the fossil fuels. For example, solar water heaters. They've been popular here in South Florida already for quite some time because we have quite an exposure to sunlight and the sun just heats up the coil. These are not solar panels, okay? They're different types of solar panels, if you will. These are not photovoltaic cells. These panels do not produce electricity. What they do essentially is heat up the water that is conserved in this tank. So these are coils, these are water coils, and we just run water through the coils, and the sunlight passively heats up that water, just like leaving a water bottle, a glass of water outside and the sunlight for any amount of time, it's gonna heat up, right? So we have hot water. And the hot water is accumulated here, which is then used for showering and other uses in the home. So this is a solar water heater, passively heating up that water. On the other end of heating water, using electricity, okay, going from the traditional water heater tank, which is probably the second thing that uses most electricity in our homes, the first thing being the air conditioning, the water heater, and we're keeping that water heated all the time, essentially, even though we're only using it a little fraction of the 24 hours of the day for showering or for using hot water in cooking, etc. There is another system that is called a tankless water heater. It's also known by its brand name. The most popular brand name right now out there is called Titan. Titan is this little box, all right? And the Titan only heats up the water as the water goes through it. So essentially it's a coil that gets extremely hot, but regulated. And so it takes in regular tap water, normal cool tap water in, and it puts out hot water, very hot, scalding hot water that can burn your hands, you know, so you have to control it with the tap. But basically, these tankless water heaters are becoming popular. They do need a dedicated line, I think of 220 volts, not 110. So on the box, on the electrical circuit box, you may need another switch for a 220 line to be installed. Typically in homes, a 220 line would be, for example, for the dryer and the washer and dryer of the clothes. All right, the dryer will have a 220 line, which is dedicated. At any rate, these Titans are very, very cheap. Well, they're a little expensive to install initially. Again, the initial investment, but they take much less electricity. First of all, you're only heating the water when it's needed. All right, when you open the hot water tap. And also because it runs on 220, it's cheaper electricity than the 110. It's less clean and so forth. Just electrically. So it's much cheaper to run the Titans than it is the traditional water heater. If you have a home, you own your own home, you may consider switching. Just get an estimation from an electrician to give you an estimate of how much it would cost to switch your water tank, your hot water tank, which will eventually corrode and break, and you'll have to replace it every so many years. For the next replacement, consider a tankless water heater.
Excuse me, Father. Your information is not as updated. I've had the tankless water heater for almost 10 years and it uses a 110 line.
Oh, it does use 110? Great,
Yep.
Thanks. I didn't know that. Okay, excellent, even better. So, but is it a dedicated line to the switch panel, to the light switch?
No, I simply installed a plug on the outside from a line that I had inside. It goes right through. They just put an extra plug out through it and that's all it is. It's an outside grounded plug and
Okay.
I've had it, like I said, for more than 10 years.
Oh, fantastic. And you can plug other things in it too?
You can, and because it's a gasless water tank, so it actually uses my gas that I used to have, but the problem is it starts with a spark. So now I have an inverter, a solar inverter that you can use if we lose electricity. Once it starts, it will stay warm, but it won't start without that first spark.
Oh, so it runs on gas actually.
Yes.
Oh, that's interesting. Okay, interesting. Okay, yeah, I think the Titan is fully electric, but I don't think it requires a gas installation. Some homes have gas access, some don't. But anyway, it's great. It's an innovative technology, and to my mind, the biggest advantage of this is that it only produces the hot water when you need it. It doesn't have a tank that you're keeping hot all the time, and most of the time in 24 hours, most of the time we're not using that hot water. Okay. All right, moving forward then for insulation of the house itself or ventilation in the north, depending on the orientation of the house can be designed so that it's oriented toward the exposure of the sun in the first half of the day, and then that sun can passively heat up the house inside, all right? Mostly if light comes in through what is known as a clear story up here above this, you notice that these two ceilings are displaced, the two roofs, the rooftops, so that there is this clear area running alongside the top of the house. And that's called a clear story. Light will come through and eventually it basically makes the same as a greenhouse effect, that it comes through the glass and that light, as it bounces around inside the house, some of it will transform into heat, and that heat can be captured and used for maintaining the house warm. This works well, especially in houses up north in the wintertime. Well, the light exposure, the glass exposure will be toward the south where the sun is shining, okay? We have the opposite for houses down here in the tropics and subtropics, where the openings of the house will be oriented opposite the sunlight, so that when we open that clear story, it will actually allow warm air to ventilate out, because warm air rises and you can get a breeze to go through from the porch, let's say, which is covered, so it's already cooled air coming through the house and passively cooling the house. If we open some slots at the top, at the very top of the house near the ceiling, then that warm air would move out passively, okay? Some of this effect is also done by those ventilators, those vents that you see on the rooftop that are kind of round, and they have inside, they have like a little propeller, and it turns passively because that's picking up heat from the house going through literally through the roof into that cone, and then just dissipating out into the atmosphere. So that also is used for cooling. That's used for cooling more. I've seen it in houses also, but also in warehouses and more commercial places that are closed in, all right? But porches tend to, especially enclosed porches, tend to cool the air because it's no longer exposed to the sun directly, and then that air can circulate through the house and cool the house. Also, keeping trees on the sunny side of the house, which will produce natural shade for the house. These are designs that are trying to use the passive movement of air to keep the house cool. This works better houses down here in a more tropic or temperate region, and this works better in the northern regions. Okay, so with architecture, a lot can be done also to try to passively heat or cool a house. One can be more proactive in the architecture and the engineering and go to these LEED buildings, L-E-E-D buildings, all right? And this is a standard that has been established now that is known as Leadership in Energy and Environmental Design. So that's the acronym is LEED. I can tell you that these LEED buildings cost more to build because of the standards that they have. But in the end, the idea is that these buildings are seen as investments because in the long run, they save on energy, they save on electricity, they save on air conditioning or heating, depending on where the building is, all right? And there are these standards of certification by levels. It works on a point system. And also there are incentives. There are like tax incentives and tax breaks for LEED building. I can tell you also when this building was built in the science building at St. Thomas University about 10 years ago now, they looked at the possibility of making it a LEED building, but it was just too expensive at the time. They couldn't afford it with the budget, so they desisted that idea, unfortunately, because now, you know, in the long run, we end up paying more for electricity, we end up paying more for air conditioning and heating and everything else. It's not just that, it's also the water system. Everything is looked at, all right? Everything is looked at the building, whether it's residential or commercial or industrial. This one apparently has one of the highest ratings. It's a tower in Taiwan. That is, the whole building is a LEED building, all right? Initially, it costs more, it's more expensive to build, but the idea is that in the long run, it will save money for the people. And so, and it's also, they're green, so they're more conscious about how they deal with the wastewater and so forth. Okay, so this is another standard. I just want to mention briefly these LEED buildings. Again, they cost more initially, but in the end, they're more eco-friendly overall, all right? Let's move forward a little bit. We can also continue to expand our minds and creativity, as a number of people are doing that already. About 4 years ago, the first solar flight, a plane that is powered only by solar panels, went around the world. You may have followed this in the news. It did it by stages. It had to land and fly and land again and fly. But this is known as Solar Impulse 2. You can Google it also and see some videos that are pretty cool. It was 1 or 2 men, I think, that were piloting it, but they went around the world in stages. And here you can see this photograph taken above the clouds. These are all solar panels, of course, on the big wing and the small wing. You can see it passing above the, this is what, the San Francisco Bridge, right? Known typically by that, I recognize it by that big red structure. It's very striking. Anyway, so this thing flew around the world already. And so it's what we call proof of principle, right? That it can be done. Of course, it has to be scaled up big time, but it can be done, all right? In fact, the largest artifact that humans have ever built is the International Space Station, known as the ISS, the International Space Station, which is a collaboration of several countries of the world. In fact, just a couple of weeks ago, some astronauts were sent up here precisely with that takeoff from the atmosphere, from a flight takeoff. And it's an international collaboration. It's essentially a scientific station where experiments are run in zero gravity. And it is fueled, the entire station is fueled by solar panels, which you can see here. Again, you take up to maintain the scale of things, you know, each one of these little tiny squares or rectangles would be about the size of a human being. So you can see the scale of the station, the ISS. It was started just before the turn of the century. And I've heard also that it's beginning to become obsolete. In other words, the structure, it's getting kind of old. And in a few years, it may be dismantled and brought back to the atmosphere for essentially evaporating through the atmosphere, dissolving it as it gains speed by gravity. Just like it happens with meteorites, that they break up in the atmosphere, thanks be to God, so that the impact is minimal or negligible. And again, statistically, on average, any little tiny part that would remain of this or a meteorite likely is going to end up on the ocean, because 3/4 of the surface are ocean. Just to point out also, the atmosphere is that thin layer that you see here, the thin blue, all right? And that little thin blue is what's literally keeping us alive because of the filtering of the UV and all the impact of the meteorites that we're having on a daily basis. You know, our surface, the moon is about the same age as the Earth. About 4.5 billion years ago, we picked it up more or less by that coalescing process. But look at how the moon looks, all right, the surface of the moon that we can see graphically just with the naked eye from Earth. Our surface should look exactly like the moon, and it doesn't at all. Rather, it is this beautiful blue, shades of blue that allow for the life that we know, the organic life that we know. So this little thin layer is precious, and it behooves us to maintain it and to keep it and not to destroy it, okay? All right, moving forward, one last thing, okay. A little more to our concern from the Catholic perspective. As recently as 2 years ago, almost to the day, this was a meeting that Pope Francis managed to gather the CEOs of mostly oil and gas companies of the world, okay? Among the highest ones are Exxon, which ExxonMobil is, I didn't know they were a single company. Eni is the Ente Nazionale Italiana. This is the Italian oil company, which is national, it's owned by the government, okay? Or maybe it's private, but it's a single oil company, petroleum company in Italy, Eni. British Petroleum, Dutch Shell, this what used to be Shell, just straight up Shell, okay? It's now owned by the Dutch. Norway also has a big oil and gas because of the North Atlantic, where they're pulling petroleum out of the North Atlantic, okay, and natural gas. And then Pemex, which is Petróleos Mexicanos from Mexico, another big, these are huge oil companies, petroleum companies in the world. Their CEOs and 36 others are sitting here in front of us, in front of Pope Francis, as he is inviting them to form this core of a group that envisions the transformation, the transition away from fossil fuels into renewable energy. And it's happening. It's really happening. You know, a lot of these companies also have their research on renewable energy resources, alternative energy resources, okay? So this is something positive, and he is really on fire with the environment and moving us forward in that respect. Also a consequence of Laudato Si that we have covered in different parts of the program, which was published in 2015, the first encyclical in the history of the Catholic Church devoted to the environment, okay, to preservation of the environment. Okay, I just want to end with this slide here that hopefully this has stimulated your creativity to think positively about changing. It involves our lifestyles for sure, but we can concentrate on the positive that we can do, trying to be as realistic as possible that we do need to make it economically feasible, because otherwise industry is not going to go for it. But also to try to be responsible in our voting and whatnot, because politics does move economics, okay? And technology also moves economics. These are all factors that play into it. At the end of the day, we're all consumers one way or another. We can be more responsible consumers with regards to the environment, but also thinking creatively. Some of you may consider going into a career that will focus on innovation for being more eco-friendly. So I leave you with this thought, right, that our creativity really has no bounds. Like they say, the sky is the limit, the space is the limit, so we can put it to good use. And just important, I was thinking here, the Earth as a whole, excuse me, essential activity going on, right? The magnetic field of the Earth as a whole. And we know that electromagnetism is one of the 4 fundamental forces of nature in the universe. So for all that I know, at some point, even this magnetic field could be harnessed at some point to generate electricity, energy, power for the Earth, all right? And so in doing so, let's hope that the poor, the ones who have less access in general to anything, will also be included in that equation, so that we make for a better world overall, and definitely move away from renewable energy sources, okay? Okay, folks, that's all I have. I've gone over a little bit, but so any questions, comments, anything as we part?
Right, Father, even though you were talking about resources, you really didn't, unless I missed it completely, anything about even a meatless Monday. Cutting down on our beef and lamb consumption could make a huge amount of difference, and a lot of places do practice a meatless Monday, you know, in addition to giving up meat during Lent. And you also didn't mention bicycles.
Right. Yeah, I did mention bicycle passing very briefly. However, yeah, so it could be a meet like Tuesday or Wednesday or Friday or the whole week, right? So these are definitely options, or personal options. Again, I go back to the teeth that we have, that we're heterodonts, and that means that, but these are choices that people can make for sure. It's not directly related to energy production and consumption, which is the topic of this lecture. But absolutely, I support it. I support anything that is going to be in favor of the environment, that is realistic also and reasonable, right?
Well, Father, I was just pointing out that, I mean, if the church took an active role, more active, the parish, the diocese, you know, they could do something even just voluntarily and encouraging people to give up meat one day. I mean,
yeah,
that's
the church does that. We're supposed to be not eating meat on Fridays.
Okay.
And that's way before. This is a tradition that goes back into the Middle Ages. Actually, it was not at all for ecological reasons. Okay, we have to be clear on that and be honest to the truth, that the meatless Friday or the fish on Friday, which is a type of animal protein at the end of the day, is because fish was supposed to be cheaper and less tasty than meat, than beef, all right? And we tend to have a desire, be fond of beef, especially the charcoal beef, the barbecue. So it was done more in the spirit of sacrifice than ecological reasons. Of course, now today people use it for ecological reasons and other reasons, and health benefits, to cut down on your cholesterol, et cetera, et cetera. But yeah, the reasons may have changed, but it's there, okay? These are personal choices that people make, and we can encourage them. At the end of the day, it's about eating a healthy diet. I didn't mention exercising, which uses up calories, right? But obviously, we also need to keep a healthy lifestyle and exercise on a regular basis and so forth. So many other issues. I think we can incorporate some of these other collateral issues, if you will. I'm sorry, someone has a mic on here. I don't know who has a microphone. Oh, thank you. Yeah, don't worry. There are a couple of other lectures coming up, and especially the one on population and population density, where I'm going to be focusing more on human behavior, okay, and how we can make a positive contribution to the current state of affairs of this Earth of ours that we call home, to try to protect it, certainly, and be good stewards and not destroy it in the process, okay? Okay, folks, well, thanks again. I'll send you this one, and if those little videos, you were not able to see them for your particular computer, just go and use the link, all right? They're short, and I think they're very on the positive side. So I'm gonna close the recording now and turn this into a YouTube. Let me see, just before I do that, this last chat here. Oh, the slide is blurry. Okay, yeah. Oh, sorry, because I left, yes, I forgot to take off the optimization. Thank you, Marie, for reminding me. Let me see, is that better now? Yeah. Okay, did it clear up?
Yes.
Yes.
All right, so probably it's gonna be blurry from the videos down, from the two little videos, because I forgot to de-optimize, to unoptimize for video. But as always, I send you the PowerPoint anyway, so you can follow with the PowerPoint, okay? All right, thanks again. Have a good rest of the week, and God willing, we'll meet again next Saturday. All the best now. Bye-bye.
Okay, bye-bye.